Hello, hello. Hello, everyone. Good evening, wherever you are. Yeah, there's so much construction noise outside. I'm sure you can hear it, and I'm really sorry about that. I hope it stops soon. It's already 7 p.m., so they should hopefully stop soon. So, today, no, wait, a few things in order. First of all, yesterday I had here a tripod that was holding the overhead camera. However, today my rigging setup arrived. So now I have this arm that is coming from here, from a shelf going out over here. So I have a new overhead camera setup. So let me quickly switch to the overhead camera for you to see the new setup. So in that way it looks kind of like yesterday. We have again the workspace where we can work, and we have up here the oscilloscope that we can look at. So I think it's pretty neat this way. I think it looks better. What else? I guess that's about it that changed. So in today's stream, we will continue with Ben Eater's series, and the thing is, the next few videos are him explaining certain types of flip-flops. If I look here in the playlist, he will talk about the SR latch, the D latch, and the D flip-flop. So I assume these are mostly just educational videos, not necessarily where we will continue the build. So that means that we will probably just lay back for a little bit, and I will be a reaction streamer. We will just watch these videos together and try to learn from them. For completeness sake, I definitely want to watch them, and I will also probably learn stuff from it. So my background knowledge about this is actually from school. I went to a technical school before I went to university, and at that school we did learn the basics of electronics. So we learned like how to simplify gates, truth tables and stuff like this, and we also learned about the different kinds of flip-flops and latches and stuff like that. So that is now probably also 8-9 years ago for me, actually, at this point. Feels so old. But so this will be also a great refresher for me, and I definitely couldn't explain them myself anymore right now. So I'm really looking forward for Ben Eater explaining them, especially because Ben Eater is so much more detailed and has really great insight that he always provides in his videos. So I'm really looking forward to watching this. But this also means we will be watching these videos, and I will be quiet for most of the time. And in the meantime, I will then eat, because I haven't eaten yet. But I thought, if I have to watch these videos anyway, I can watch while we. No, wait, I can eat while we watch. So how's everybody doing? I see some people saying hi in chat. Hey, nice for you to be here. If there are any questions about the stream yesterday or anything, then let's deal with that before we then head into the videos. Hey, I'm a noob who has been learning from Udemy. My friend who has been doing this for years suggests me to learn Python first, but when I try to do exploit exercises, I see it's C language based. What should I learn first, Python or C? So first of all, what did you watch on Udemy that you still haven't learned that stuff? That's just my small criticism of Udemy. I don't think, I'm sure they are great courses, but I think the most of them are garbage. So please don't spend money on them. I think my videos provide more value than most Udemy courses, and my videos are free. So it always kind of annoys me and makes me mad that people would spend $10 on Udemy courses because they cost money. There must be more value, but then they are shit. While you can get my videos for free, or even just support a little bit on Patreon with like $1 per video or something like that. Just my small rant, I'm sorry. But well, it depends on what you want to do with exploiting. Exploiting is a broad term. Typically, or usually how I refer to it, especially in context of my channel, I talk about like the series I have on binary exploitation is mostly about small C programs. But in reality, exploiting could mean anything. It could be web application exploitation, or it could be compiled programs. But then it also depends on with what language this program was compiled. Exploiting programs written in C++ are somewhat different than just raw in C. But I think C is the simplest way to learn about this kind of low-level exploitation. C++ just kind of adds on top of that with different kind of language features that you can abuse during your path of exploitation, and a few different kind of primitives that exist in these other kinds of languages. So I think that's the way to think. Now, also, I don't think what should you learn first, Python or C? Why do you even make this distinction? Just learn what comes up. When you see a problem that you need to solve, then you learn the tool that helps you to solve this. So if you want to write a script that does something, then is the moment you learn Python. And if you want to learn a bit about like exploitation, this kind of, these basics of exploitation with C, then you learn C. And now you maybe need to write an exploit script to exploit what you want to, what you have written in C, then is the point when you learn Python. So don't think that you need these blocks. Now I need to learn Python and now I need to learn C, and which one do I do first? It's all intertwined, it's all interconnected. You jump between those topics all the time. So I think that's the better way to approach this. And my recommendation would be, of course, I'm a bit biased, or I also don't have a lot of, I can't compare much, but I think you can just start with my binary exploitation series, and it is it used to be exploitexercises.com, but it's now called exploit.education. That's the website that my videos are about. So you can follow along, you can install this, you can try them yourself. When you get stuck, you can watch my videos and try to do it yourself. Also, don't get stuck on the videos. Even if you feel kind of stuck, keep watching a few videos, because this is the problem. A lot of these knowledge information things have kind of circle references. So sometimes certain early videos become clearer once you watch the later video. So just feel free to explore. Don't be scared. Play around with it. Along the way, you will maybe write a little bit of Python or a little bit of C. That's my little rant there. I watched all his playlists. I wonder, do you want to improve his computer after finishing, adding more RAM? Yeah, and assembler operations. That's also my plan. I haven't watched the series yet, but I did hear that it has only 16 bytes and limited instructions. So that's exactly something that once I feel, I'm also learning here. So once I feel more comfortable and understand it better, then that's definitely like a challenge or a thing to work on to increase the memory and also add more instructions for sure. Actually, basics in C you can learn fast, at least to understand the basics. Yeah, for sure. C is in some way a very simple language. There are not many things. Yes, I've been doing the education sites Nebula. It's very interesting. Yeah, perfect. You're on a good path. Don't worry about it. Keep doing. That's great. That's exactly what you should be doing. All right. And please don't waste any more money on Udemy courses. Please, please, please. Do this, what you are doing. Play kind of sites like Exploit Education, like Nebula challenges or whatever. Go that path. Check out Pico CTF. Check out all the other CTF websites. Don't worry too much about which CTF. You just need to get started and play them and get stuck and get frustrated. That goes way more than any course. All right. Okay. Cool. So let me switch here the screen to the laptop so that is working. Awesome. Let me put myself somewhere up here, I guess. Oh my gosh, they do street construction work outside, so the whole apartment building is shaking. I'm like on a upper floor and I still feel the floor shaking. Okay. Everybody ready? Watch some YouTube videos while I eat. All right. Also, if the audio and stuff. Oh, and by the way, I should have also fixed the alerts. Yesterday they didn't make any sounds. I hope now today they make sounds. All right, let's watch the next video, the SR latch video.
So in previous videos, we've looked at the OR gate, which if you remember, in this case, if we have two inputs, if one input or the other, or both, are on, then the output is on. Otherwise, the output is off. In this video, I want to start thinking about scenarios where we have a gate where the output is connected back to the input, or some series of gates where the output is connected back to the input. And so you might think, well, maybe we can just come up with a truth table like this, where the input can be either a 0 or a 1. If it's a 0, then the output ought to be something, and if the 1, the output might be something different. But what we'll see is that it's not quite as simple as that. So to build a little bit of intuition for what's going on here, I think it's easiest to kind of build a circuit and kind of see what happens. So this is that circuit. It's got this chip is a 74LS32 chip, which has 4 OR gates on it. And this is the pinout for it. And you can see with the 4 OR gates, you've got A, B, and Y are the input A, input B, and Y is the output. So the first 3 pins. And this chip is upside down, so it's these first 3 pins here. And what we've got, just like the diagram here, is input A is connected to this switch. Input B is connected via this little blue wire to the output. And then we also have an LED connected to the output. And you might be wondering if we need a resistor for this LED, but if we look again at the data sheet for the 74LS32, there's already on the output, there's already a resistor here connected through this transistor. And so when this is switched on, the gate's on, we already have this 120 ohm resistor built into the chip here in this case that's going to limit current. So we should be okay with that LED. The input is connected to this switch, which it's actually connected across this resistor to ground. And then when we push the button will connect us to this 5-volt source here. So if we're not pushing the button, it's inputting a 0. If we push the button, it's inputting a 1. And this is a momentary switch. So let's hook the power up and see what happens. So hook the power up, and you can see the output is off. And so that kind of makes sense. Maybe the inputs start as zeros, and so 0 and 0 should give us a 0 output. And of course, if that's a 0, then that's going to feed another 0 back into this B. So it just stays, everything's a 0. So that makes sense. So now let's see what happens if we change the input to a 1 by pushing the button. So if we push the button, the input's a 1, so a 1 and a 0. And we get a 1 as the output, and we see the output comes on. But actually, this output is now coming back into this input, so B is a 1 as well now. So actually, we're pushing the button, so we've got a 1 coming in A, we've got a 1 in B, and so the output is still 1. But now if I let go of the button, so A is now 0, B is still 1, and so the output is still 1. And so this stays on, even though I've now let go of the button. And in fact, if I keep pushing the button, there's really nothing I can do to get this to turn off. Once this input turns on, even if it turns off later, the output stays on. It latches on, essentially. And so really the only way to reset this is to disconnect power from the entire circuit. And then we can reconnect it, and then of course it starts out at 0 again. But if at any point after this thing is powered up, that input ever goes to a 1, even if it's just momentary, if I just hit it really quickly, that output latches on and remembers that input was at one point a 1. So this is pretty interesting, and you can imagine why we can't just come up with a simple truth table like this, like we might like to. But what would be even more interesting is if we had some way to turn it off again, some other way to reset this other than having to disconnect power from the entire circuit, because that might not be too practical. So what I want to do is look at another circuit that actually does work that way. And this is that other circuit. And this might look a little confusing at first, but we'll walk through it. One thing you'll notice is different. We're using NOR gates instead of OR gates. So it's the same as an OR gate, but the output is inverted. We'll talk a little bit more in a minute about that. And again, I think a good way to build some intuition for this is to actually build the circuit. And so I've done that here. This chip now is a quad NOR gate. It's a 74LS02 chip, which has 4 NOR gates. And of course, we're just using 2 of them. And to kind of walk through what's going on in here, the bottom pin here is this bottom input. And then the next pin up is this input here. And you can see the yellow wire is connecting it to the output of the top NOR gate. The third pin is the output of the bottom NOR gate here. And you can see that's connected to an LED, so we can see what the output is. And you also see this little yellow wire is connecting it to the input of the top NOR gate. The other input at the top NOR gate is connected through this blue wire to the switch here, so we can set the input there. And then finally, the output of the top NOR gate, as we saw, we've got it hooked to an LED here, and it's also going back down to an input on the bottom NOR gate. And again, these switches are hooked up so that they're normally a 0, and when we're pushing them, they're a 1. So let's, before we think too much about this, let's just sort of power this up and see what happens. I always like to kind of build the thing and see what happens. So we plug it in, and the top LED comes on. So this NOR gate on the top is switched on. So this is basically what is happening here. So I've kind of drawn exactly what states different things are in to kind of make this a little bit easier to understand. And also as a reminder, I've got the truth table for a NOR gate. So again, if either one input or the other or both are on, then it's off. Otherwise it's on. So it's sort of the opposite output of an OR gate. So in this case, the top OR gate is on. And so we see the LED there. And that implies that this input down here must also be on. And so if we just kind of reason through this, hopefully it'll make sense. So the bottom NOR gate, we've got a 1 and a 0. And of course this one, for some reason, this top LED came on. We'll talk about why a little bit later. But for now, we'll just sort of take it on faith that it's on because we can see that it's on. And the bottom is 0 because we're not pushing this button. So that's a 0. So a 1 and a 0 means that the output is a 0. And that makes sense that we see the bottom LED is off. And so then that's being fed back into the top NOR gate. And of course, we know we're not pushing the top switch either. So it's a 0 and a 0 going in here, which means that the top NOR gate should be on. And that's what we see. So this hopefully makes some sense. So now what happens if we start changing these inputs? So the bottom input is fairly straightforward. If we turn the bottom input on, then this gate will be, the inputs will be 1 and 1. And we can see the output then is still 0. So this doesn't change, which means this top, nothing else changes. So if we change this bottom, if we input a 1, if we push this button, nothing should happen. And in fact, nothing happens. We can push this button as much as we want. Nothing's changing because we're just going from 1, 0 to 1, 1. You can see 1, 0, 1, 1. The output stays the same here. Doesn't change this. Nothing changes. Now the top one is a little bit more interesting. So if we push the top button, we're basically changing this here to a 1. So I've just redrawn the circuit here, and I'm changing just this top input to a 1. Well, if we do that, the top gate now has inputs of 1 and 0. And so 1 and 0, it ought to turn off and output a 0 here. Well, if it does that, that puts us here. So 1 and 0 and 0. So that makes sense. But now that changes the input of the bottom gate. And so now the bottom gate is getting a 0 and a 0 coming in. Well, if a 0 and a 0 are coming in, the bottom gate ought to be outputting a 1. So then it's going to switch on. And when it switches on, that changes the input on the top gate again. So now the top gate is getting a 1 and a 1. Well, in that case, a 1 and a 1 is still a 0. So the top gate doesn't switch. It's already off. And so now the circuit is stabilized in this configuration. But what you see happens is before we had the top LED on or the top gate on, and at the end of this whole sequence of events, the bottom gate is on, the top gate is off. So let's give it a try. I push the button here on the top. Indeed, we see the top goes off, the bottom comes on. So we're now in this state. And really, it did actually flip through all three of these states. It just happened very quickly. I mean, on the order of nanoseconds, really, to get to this state here. Well, now if we release the top button and this goes to a 0, that puts us in this state here. And a 0 and a 1 input on the top gate is still going to output a 0. So a 0 and a 1 is still a 0, and so nothing changes. And so now with both inputs off, we've swapped which of the gates is on. So this is essentially a mirror image of where we started. So we started with the top gate on, the bottom gate off. Now we have the the top gate off and the bottom gate on. And since this is the mirror image of this, now pushing the top button doesn't have any effect. Whereas before, remember when we were pushing the bottom button, it didn't have any effect. But pushing the bottom button is basically going to run through this same sequence of events, but sort of in mirror image, and flip from the bottom to the top. And now the bottom doesn't have an effect. And so you can see by pushing these buttons, we can kind of flip it between one state and the other. And then once it's in that state, it stays in that state until we push the button again, or until we push the other button, I should say. And so this is a fairly common circuit, and it has a name. It's called an SR latch. And SR stands for set reset. because the latch can essentially be set or reset. And so these inputs are labeled, typically labeled R, S, and then the outputs are labeled Q and inverse Q or not Q. And the way to sort of think about this is that if you want to set the Q output, then you input a 1 on the S input, or the set input. So this sets it in the sense that the output Q is on, and then this resets it in the sense that the output Q is off. And then inverse Q is just always the opposite of whatever Q is. And so sometimes you might see this this SR latch in circuit diagrams just as a box. They'll draw it like this, and it'll have these inputs, and they'll be labeled R and S, and that's how you'll know it's an SR latch. And it'll have the outputs Q and not Q, and then usually they'll have a little bubble here to show that that's an inverted output. And so if you see this in a circuit diagram, you can basically think of it as this circuit, or something that works equivalently, in the sense that if you press if you input a 1 on that set input, then the Q will latch high. And if you input a 1 on the reset input, then the Q will latch low, and then the not Q will sort of do the opposite. And you might be wondering, what happens if you input a 1 on both the set and reset at the same time? And in that case, the outputs are both Q and not Q go low. And sometimes you might see this referred to as an invalid state, because if you're sort of using this as a set reset latch, you should only be setting it or resetting it at any point in time. You shouldn't be doing both. So sometimes you might see that as an invalid state. So the other question you might have is, when we first powered this up, it started with this top gate on and the bottom gate off, and you might be wondering, well, why did it prefer the top gate? This circuit is fairly symmetrical, and really it's just kind of almost random or arbitrary which one turns on first, because when it first starts up, all of these inputs are zeros. And so if both inputs are zeros, both gates want to turn on. And in fact, both gates might turn on, but what will happen is one of them will turn on maybe a little bit faster, and this signal will get to the other gate, and this other gate will now have this one input, and a 1 and a 0 will turn one of the gates off. And so it's really just a question of which one turns on first. And it's, usually, it's probably on the order of a few nanoseconds, or one is just a little bit faster than the other. And so it just sort of arbitrarily, one of them is going to turn on first. And so, if you're using this circuit or if you're using this, this SR latch in a circuit, you're going to want to make sure you have some way of resetting it or setting it or getting it into some known state before you rely on its output, I suppose. And so because the SR latch has this property that you can set and reset it, and it remembers the state that it's in, you can imagine it might be useful in all sorts of computer memory and other applications. And so in future videos, we'll build on this and look at some other types of latches and other components that are used in computers. So in the last video, we took a look at the SR latch.
Excellent. So that was the first video. Yeah, my big cups, I love them. They are from the US. I was introduced to them in Texas, and so they have like this double wall, and they keep the drinks fairly cool. So they were drinking it during barbecue, and I thought they are so amazing. And then I had to buy a couple and bring them with. Now this one specifically has a stormtrooper as a design. Yeah, and they have saved my life a couple of times because of the lid. It's not like completely sealed or anything. It leaks out. It has an opening here for the straw and stuff. But if it just falls over a little bit, it just spills a couple of sprinkles, and I have, thrown this over my, accidentally knocked it over while working on the desk, and so it keeps it cold and it keeps it safe. Sorry, allergies. I have this nasty cough and my nose is itching. So you are making this latch, but what for? No, I'm not. We are watching Ben Eater's videos on the 8-bit computer, and this was just the next video in the series. So before we move on to the next module, he's explaining what the underlying stuff that we will be using next. I assume that's the reason. The SR latch, and the flip-flops and stuff like that, that is crucial information or knowledge to understand how the computer then later works. These are the kinds of components that we will make use of. So he's explaining them now, and so we watch these videos before we can move on. So I don't plan to implement this here now myself. Just watch it. Yeah. So these are Ben Eater videos, just FYI for the people who have been asking what this channel is. Ben Eater is the person who built this 8-bit computer, and he has this playlist, this series on it, which I'm following and want to implement myself. Okay, so feel free to write some questions after the next video. I will again pause and we can have a quick chat before we then move on. I think there are overall 3 videos of that just explanatory kind, and then the 4th one will be continuing here. So yeah, let's head back in.
Which is this latch that has 2 inputs, a set input and a reset input. And if we input a 1 on the set input, it sets the latch and the Q output goes high. And then if we input a 1 on the reset, it resets the latch and the Q output goes low. So in this video, I want to look at trying to build a latch that has a single input. So instead of having one input to reset it and another input to set it, having a single input that when it's a 0, it resets it, and when that input is a 1, it sets it. So you might think, well, that's easy. We can just put an inverter here. And so if our input is a 1, then it sets it. And of course, our input's inverted, so the reset's a 0. And if our input's a 0, then it's not setting it. But if we invert that 0, we get a 1 up here and it resets it. So let's try and build this and see what happens. So here is the circuit, and basically it's the same as before. So we've got the 2 NOR gates here connected just like this, and then the set input is connected here to this button, to our single input. And then the button is also connected through an inverter to the reset. And so this is the reset up here, and it goes through an inverter. And to invert, I'm using this NOR gate. So this chip has 4 NOR gates on it. And so rather than having another chip that has an inverter on it, you can actually use a NOR gate as an inverter, because if you look at the truth table for the NOR gate, you can see if both inputs are 0, then it outputs a 1. If both inputs are 1, it outputs a 0. So if you tie both of the inputs together, you can turn a NOR gate into an inverter. So this is just kind of a little shortcut, since I've already got the NOR gates on this chip and I'm not using all 4 of them. So this switch is going into both inputs. The little jumper here connects both inputs, and then the output of this NOR gate, that's now an inverter, is going into the reset. So let's see what happens. Okay, well, the input is off and the latch is reset. So the Q is 0, the not Q is 1. And if we turn the input on, the Q goes high, so it sets it, and the not Q is low. The problem is it's not actually latching anything anymore. It's not serving as a memory or storing anything. It's just whatever the input is, then Q is the same thing, and not Q is the opposite of the input. So this is not super useful. So what we need to do is find a way to tell the latch part of this when it should latch the input and when it should just ignore the input. And so a way to do that is to have an enable option, essentially, or an enable input. And this is an example here of adding an enable to the SR latch. So this is our SR latch that we're familiar with. And instead of just having the reset and the set inputs directly go into the latch, we have them going through these AND gates. And so in order for this AND gate to output something, both inputs have to be on. So this has to be, this and this have to be on in order to get an output here. And so by using these AND gates, this gives us an enable input. And so as long as the enable input is off or 0, both of these outputs, these AND gates, are going to be 0 regardless of what the reset or set is. So this basically gives us a way to kind of turn on the latch and turn it off. So let's build this and just to kind of get a better intuition of what's going on. So this is that SR latch with enable. And so what's going on here, it's a bit more complex, but down here is our NOR gates, just like we've been seeing before. And the outputs are connected to the inputs. That's what these yellow wires are, is these cross wires here. And then the inputs, the reset and the set, are these blue wires. But instead of going directly to switches, they're now going to AND gates. And this is a 7408 quad AND gate chip. And we're using 2 of the AND gates on this chip. And so one of the AND gates outputs is going to reset, the other is going to set. The inputs are coming from either the reset button, which is this, across this green wire, or the set button, which is this button across the this other green wire. And then the enable is this button up here is connected to both, or an input of both AND gates. So this is basically a SR latch with enable. So it's just like the SR latch, but we now have this enable thing. So let's take a look at how this works. So we power it up. Looks like it's started up in the set state because Q is high, but just like the regular SR latch, it's just going to kind of randomly pick one state. And if we try to reset it or set it, you can see that pushing these has no effect, and that's because it's not enabled. What we have to do is enable it by pushing the enable option here. And now that it's enabled, the set and the reset will work just like before. We can set it and reset it. And so if we reset it and then let go of the enable, now the set and reset don't do anything. If we turn on the enable, we can set it. And then if we turn off the enable, it stays set. And now the set and reset don't do anything. So we have this SR latch that we can set and reset only when the enable is on. And so now that we have this enable option, let's try and put that inverter back in and see what we can do. So here's the same thing. We've got the set and reset here going through these AND gates. We have our enable, and now we're hooking this inverter up. And so we have a single input coming in here, and we can either set it by setting this high, which will set the latch, or we can reset it by setting it low, which will then set the reset high and the set low. But it'll only change when we've enabled it. So if we look at that circuit, we've got our NOR gates just as before. We've got them hooked up with the 2 inputs, and so this is the reset and the set inputs over here, are these blue, are the blue wires. And then they go into they come from, I should say, the AND gates, and we're using 2 AND gates here as well. And then the inputs for the AND gate, one of them is the enable, and that's this top button here. And so you can see these 2 yellow wires are going to an input on each of the 2 AND gates. And then the input, which I've labeled as D for data, I guess. The input is this second switch here, which you can see there's a green wire that's going into the input of the sort of the bottom AND gate, which is the set. And there's another green wire that goes back over here, and again we're using one of the NOR gates as an inverter, and so it's going into 2 inputs of that NOR gate, and then the output of that NOR gate, so the inverted signal from that NOR gate is then coming back into the top AND gate. So if we power it up and take a look, it powers up and it looks like it's set at the moment. I've also added an LED here, so the input, you can see whether I'm pushing the button here. And so you can see the input is changing, this input is changing, and now the output's not changing. And that's because the latch is not enabled. If we enable it by pushing the top button, you can see now that when the input changes, the output changes to follow it. But if I turn off the enable, it latches in this case reset state, and then if I turn on enable and then I set it and then I turn off enable, it now latches enabled. And so this is usually called a D-latch because it will latch a single bit of data. Because we can use this as part of to build a memory or a register or something in a computer to store 1 bit of data. And if you see, there's a block symbol for it as well, which has this block, and it has the D input, the enable input, and then the Q output as well as the not Q output, which is just always going to be the opposite of Q. And in fact, normally if we were using this to store a bit of data, we would probably just ignore this Q. And so in fact, we can do that, and we just pull the LED out, and that'll, we can basically ignore it. And so you can see what's stored in this D latch right now is a 1. And so then if I enable it, and then I change that to something else, maybe I change it to a 0, now what's stored in the D latch is a 0. And again, I can enable it, and it follows whatever the input is. And then if the input is a 1, and then we turn off the enable, the latch stores a 1. And so you can see this is a great way to store 1 bit of data as we might in a computer register or even memory or something. So in the last video, we built this D latch, which has
Crap, sorry for the microphone. Okay, so I was just saying, thanks for the cheer, NianoCat. And then about what the plan is. So the architecture here is called SAP, but it has nothing to do with the software manufacturing SAP. It's called simple as possible. So it's from as far as I know, it's out of a book explaining how a computer is, what the different parts of a computer are. And in this book, the author introduces SAP 1, 2, and 3, I think. And so these are as simple as possible architectures to build your own kind of computer. And that's what Ben Eder's videos are based on. So he has it based on this book, which I don't have. But so yeah, that's called SAP, simple as possible. So yeah. Oh, that's clever. Yeah, I think it's so fascinating, right? These gates, an AND gate or NOR gate, so easy to understand. And suddenly, once you connect an output back to an input, you open up this whole magical world of suddenly what is possible with these setups here. And then suddenly you have such a thing as this SSD latch or something. I think it's also really clever because you understood these parts, or you thought you understood them, but at least I would have never thought about, what would happen if you connect them back and what could you build out of that. I think this is real ingenuity. Thanks for the cheer, Slice. Dinner plus streaming time. Yeah, I also just ate dinner. I'm not sure if you were here, but while we watched the first video, I ate my bowl. Still too big for an i7. What do you mean? Turn on audio. Yeah, sorry. This is just a mini lecture in electronics. Well, not by me, but by Ben Eder, of course. It's to make a register, probably. Yeah, let's us maybe peek forward. What is the next video in the series? It will be the bus architecture and how register transfers work. Yeah, so I guess we will head into the registers next. And the bus. But first we need to watch the third video, the flip-flop video. Your 1 bit of data is 3 times bigger than I said. Oh, yeah, that's true. Isn't it insane what you can put on these small chips? Really makes you appreciate it once you see like the gates in more human size. I don't know. All right. I hope everybody's doing fine today. How is everyone? Now a few more people have joined since we started. Human sized, yeah. I think if you grind open or etch these open, you might be able to see them with, you might be able to make out the gates of these simple AND and NOR gates maybe with even a lens, maybe, possibly. I'm thinking about building this during my master's break as well. Sounds fun. Oh yeah, I think it's a lot of fun. I also think it takes a lot of time, but it has also something meditative about it. But yeah, I think it's a cool project. I always wanted to do it. No Club Mate today. I might get a Club Mate after I drank my cola. Meditative. All right. Yeah. Okay, then let's quickly watch the next video. Oh, it's 16 minutes. Oh, well. Let's get it over with.
Has the enable input as well as the D input, and whenever the enable input is high, then the output here, the Q output, is just equal to whatever the D input is. And then there's also an inverted Q output, or a complementary or negative Q output that's always just the opposite of what Q is. And then if the enable is not high, then it doesn't matter what happens with the D input. So this is the D latch. I've made a slight modification from the circuit we had in the last video, which is that on the inputs I've added these LEDs. And so if we're not pushing the button, then this is going to be very close to 0 volts. It'll sink a little bit of current through the LED, but not enough to light the LED up. And then when we push the button, then we're connecting 5 volts to the input, and so the input goes from 0 volts to 5 volts. And then we also have 5 volts that can flow through the LED, and this resistor just limits the current through the LED so we don't burn up the LED. And so I just added these LEDs so that we can see what the inputs are. So to get a better sense of how this works, we can look at a timing diagram, which is this here, which shows the values of the inputs, the enable input and the D input over time. And so it shows them going high and low, and we can see, we can kind of think through what's going to happen to the Q output. And I've left off the inverted Q output because I think it's just kind of distracting, but in fact I'll remove this LED. But just keep in mind that the D latch also has an inverted output that's just always going to be the opposite of whatever Q is. So remember, the way this works is whenever the enable input is high, the Q output is just going to follow whatever the D input is. So just for these periods of time where the enable is high, the Q is just going to be what the D is. So the Q here is going to be just what the D input is. And then the rest of the time, when the enable is low, the Q output is just going to stay whatever it is. So if it starts out off, for example, it's just going to stay off. Here it's off, and so it's just going to stay off. And then here it's just going to stay off. And in this case, it's going to stay on. And in this case, it'll stay off. So it doesn't matter, during these periods what the enable or what the D input is doing. As long as the enable is off, it's just going to stay latched wherever it is. So if we want, we can just verify that this works the way that we think it should.
He had to practice that. That's like almost playing like piano.
Yeah, and it looks like it works the way we would expect. So that's great, and hopefully it makes sense to you how that works. But oftentimes in more complex digital logic circuits, we've got lots and lots of different latches that are latching different values all over the place. And it's important to keep all of that in sync. And so typically there is a clock of some sort that is controlling the operation of all of the different components and keeping everything synchronized. And it's important, what you want is you want to be able to latch the values at a particular point in that clock cycle, not necessarily just transparently passing through the values anytime that clock signal is on. And so to do this, we'll look at a variation of the latch, which is the flip-flop. So with the D latch, anytime it's enabled, the input D is going to be output at Q. And so if the D input changes while the latch is enabled, then you'll see a change at the output. But oftentimes what's more useful is to think of instead of having an enable input, having a clock input, and then only outputting a change just at the point where the clock transitions from low to high. And so this clock is really more of kind of a heartbeat that says at these specific points in time, that's when I want the latch to latch in or change its value. And so for example, at this point here where the latch transitions from low to high, that means we want to take this value right here at D and we want that as our output. So that's a high output. So if we were already low, then we would transition to high at that point there. And then we want to not do anything. So even though the D input changes while the clock is still high, we don't care. All we care about is when the next clock pulse is, which is the next pulse from low to high. And then we want to take this value. And that happens to be high, and so in this case the latch won't switch. And so it'll stay high here. And then we say we don't care about anything that happens, even though it goes low and this is still high here, we don't do anything, because all we're doing is we're looking for that next transition from low to high, that next clock pulse. And that happens here, where D is low. And so at that point in time, we'll switch the latch off. And then again, we don't care what happens here, it goes high again, whatever, we don't care. We're looking for that next clock pulse where it goes from low to high. And in that case, the D input is high, and so at that time, we will switch the latch back on. And in this case, there's no more transition, so we just stay high. And so you'll notice this is a very different output than we got with this scenario where we're using the enable. But it turns out this is actually far more common. It's far more common to want to only switch at a particular instant in time. So the question is, how do we build a circuit that does this? Well, one way would be is if we could build a circuit that could take this clock input and turn it into essentially something that would be useful as an enable input for normal D latch. So to kind of give an example of what I'm talking about there is, imagine we could take this clock signal and get a signal out, put it into some circuit, and then get a signal out that had these really quick pulses just at this point where the clock transitions from low to high. So if we could build a circuit that could do this, then we could use this new signal here at the top as an enable for just the classic D latch that we've been looking at so far. And as long as this pulse is really, really narrow, then effectively we're getting an instantaneous, or as close to instantaneous as we can, kind of readout of what D is and transitioning just at that point. And so if you look at this is kind of like your enable in a regular D latch. And then if you have that enable and that D, you put that into a regular D latch, then this is the output you'll get. And hopefully that makes sense. And so you can see if we could somehow take this clock signal and detect these rising edges with a circuit that we'll call an edge detector, and detect those edges and then turn that into a pulse like this, then we can build what's called a D flip-flop, which is a circuit that will take, that will start with this clock and only transition at these points where the clock transitions from low to high. So now the question is, how can we build an edge detector circuit that takes this clock signal and outputs these pulses? Well, there's a couple ways to do it, and one is this sort of interesting looking circuit here. And you might be wondering, well, what does this do? We've got one input and one output, and so the idea is that somehow a rising edge here is going to result in a pulse over here. But you might be wondering, well, we've got this inverter going into an AND gate, and so we have an input here going through an inverter, and one side's going through the inverter, the other side isn't. So if you had, let's say you had a 0 over here, well, that 0, if you have a 0 coming in, it's a 0 over here, it's going to be a 1 over here. And then, the AND gate's going to be a 0. It's only going to be a 1 if both inputs are 1s. And you might wonder, well, how do you get to both inputs being 1? I mean, if this is a 0, then this is going to be a 1. If this is a 1, then this is going to be a 0, because we're inverting this. And so you would think this AND gate would never turn on. And you'd almost be right. But what happens is, if this signal is a 0, we have this situation here where we have a 0 coming in and a 1 here, and so the AND gate's going to be off. We're going to have a 0 coming out. But when this input transitions from a 0 to a 1, this, instead of being a 0, is going to be a 1. And then you would say, well, then this would be a 0 because we're inverting. But the inverter actually takes a small amount of time to switch states. So when this input changes from 0 to 1, we've got a 1 here immediately, but the inverter doesn't switch off for a few nanoseconds, very short amount of time, but enough time that for a very brief period of time, we've got a 1 and a 1 coming into this AND gate, which turns the AND gate on. But then, of course, very quickly, the inverter switches off. This 1 turns to a 0, and now we've got a 1 and a 0, and then, of course, the AND gate turns off. And so it turns off almost immediately. But now we have this pulse, and we get this pulse anytime this input transitions from low to high. We'll get a little pulse that comes out. And that's exactly what we wanted here in order to detect this rising edge on this clock signal. So that's one way of building an edge detector, and I would actually encourage you to try building this yourself. There's a simpler way though that I'm going to do, because this is going to require an AND gate and an inverter, potentially multiple inverters. You might find if you try to build this, you need to stack up 3 or 5 of these inverters in a row just to get enough of a delay so that you get a big enough pulse. But you can give it a try. But a much easier way to do it that doesn't require adding more chips here is to use a resistor and a capacitor. And so we can use a little circuit like this where we go into a capacitor and then through that capacitor, and then we have a resistor here that just goes to ground. And so you're wondering, well, what does this do? Well, in this case, if you've got this signal that comes in that transitions from low to high like this, when it's at 0, we've got 0 volts across this capacitor. The capacitor is discharged, because the ground here is going to be at 0. So you've got 0 volts over here. So that's not very exciting. But then when it turns on, the capacitor is going to start to charge. And as it charges, there's current flowing into it. And of course, if you've got current flowing through here, you're going to have a higher voltage here across this resistor. And so as soon as this turns on, this is going to jump up to 5 volts. Assuming this is a 5 volt transition here. But very quickly that capacitor is going to charge, and it's going to charge through this resistor. And as the capacitor charges, less and less current is going to flow into it until the capacitor becomes fully charged. And when the capacitor is fully charged, then no current is going to flow through here, and we're going to be back down at 0. And so what happens is this turns on very quickly, and then it slowly, or maybe not so slowly, depending on how fast this is, but it discharges, or excuse me, it charges, the capacitor charges, and so the voltage over here drops until, once the capacitor is fully charged, you can have 5 volts on this side, 0 volts on this side, no current flows. And so you can see this is a pretty simple circuit to take, this rising edge and turn it into a quick pulse, because then this can stay high and this will just be low. But you get this nice quick pulse right at that rising edge, which is what we want. So the question is, how quick is this pulse? And I'm not going to go into deriving all of the math, but you can calculate the width of this pulse by just multiplying the value of the capacitor and the resistor. If you multiply the value of the capacitor and resistor, it'll tell you essentially where the point, or how much time it'll take for this capacitor to get about 2/3 of the way charged, which will give you a pretty good sense of how short this gap is. So let's build this. I've got a resistor and a capacitor here. This is a 0.1 microfarad capacitor, and then this is a 1K resistor. And so if we want to figure out this time constant, to figure out how big this pulse is, we can just multiply these together. But of course, we've got to get them into standard farads and ohms. So 0.1 microfarads is going to be 0.1 times 10 to the minus 6. And then 1K, of course, is just 10 to the third. And so if we take 0.1 times 10 to the minus 6, multiply that by 10 to the third, we get 0.1 times 10 to the minus third, which is going to be equal to 0.1 milliseconds. Because if you're multiplying farads times kiloohms in this sort of circuit, you end up with seconds. And so 0.1 milliseconds is how long this gap will be. So for our purposes, we can say that, okay, 0.1 milliseconds is, pretty much instantaneous, which is what we're going for here. We're looking for, when this clock transitions, we just sort of take an instantaneous read of this D input. So as long as in our circuit, this D isn't transitioning anywhere near, every 0.1 milliseconds, then we'll be fine. And of course, in this case, we've got a button here. I'm not pushing it any faster than that, so we'll be fine. So let's go ahead and build this. So right now, I've just got this little jumper here between the enable button and the enable part of the circuit. So I'm going to take that jumper out, and instead we will put this capacitor in. So that's this capacitor. So from the button we're going to get this pulse, and then of course we need this 1K resistor here going to ground, so for the capacitor to charge through. So let's give it a try and see if it works the way we would expect. And it looks like it works just the way that we would expect it to, which is great. And definitely different than the D latch. And so that's the D flip-flop. And if you look at the D flip-flop, it's basically very similar to the D latch. In fact, it's identical, except that instead of the enable, you have some sort of pulse detector. And in this case, I'm using a resistor and a capacitor. You could use this, this weird AND gate inverter thing if you wanted to, but something that's going to detect a pulse for that clock pulse. And so instead of having an enable input and a D input, you have a clock input and a D input. And in the sort of block diagram for that, the clock input is usually indicated with a little triangle here that tells you, that this is edge triggered. And so that's the D flip-flop, and that's probably the most common way of storing data in a digital logic circuit.
All right, those were the 3 videos, slowly leading up to a full flip-flop. I probably learned this in school, but I completely forgot about how the edge detection, like how a pulse is detected, how it works. I'm pretty sure we had flip-flops in school, but yeah, I completely forgot that it basically converts it into a very small pulse through something like here with a capacitor. So let's see. Welcome back, Toby. We haven't really actually done much, by the way, in those 54 minutes already of streaming. We basically just watched the 3 videos. Crazy. Yeah, I never understood resistors. What do they actually do? I don't know. That's a good way. I think the link that was shared is really useful. It's just one of these fundamental properties of electricity, I guess, that things where current is running through, or the electrons are running through, that those materials have resistance, and different materials can have different resistance, and that has a certain physical effect, or an effect on the physics. I don't know. I'm always streaming when I'm not in my PC. Well, when are you on your PC? Hi, Adriaroms. Alright. Okay. Oh gosh, I get always so tired if I'm just watching videos. Usually, so I don't know what my problem is, but I can't read books for the same reason. Like if I sit still, it doesn't work. So now the stream forces me to sit like still and just watch a video. Usually I would like browse Reddit or whatever, and without that I'm just falling asleep. Oh, greetings to Portugal. Anyway.
In the next couple of videos, we're going to focus.
Sorry. Right. Okay. So let's see. The next video is 9 minutes long. Yeah, we definitely gonna watch that as well. Yeah, any other questions? So is it a lower or upper bound? Wait, what was this question about? So you were asking about resistors, and then you followed up with, is it a lower or an upper bound? Toby, any email would work. All should reach me. Did you try to send an email? Because I don't remember getting any on either of all these kind of addresses. Because I feel like capacitors impose sort of a lower one. Math slice, sorry, I have really no clue what you're talking about right now. Yeah, you can send me any email. All right. Then I guess let's watch the next video.
On building the registers for this computer. And the registers are a fundamental building block of any computer, and we've got a couple of them in this computer, and they're fairly simple, actually.
This is, by the way, the computer we want to build here on stream. Today I haven't explained again what we are doing here, but this is basically how it looks like. And the module here that we have, here, this module here that you can see with the blinking LED, that's the top left module that you can see here on the laptop screen. This is the clock module. This is our clock. Anyway, let's continue.
Actually, they're just 3 chips. We've got a 74LS245 and a couple 74LS173s. And then we've got some LEDs to show us what data is in the register. And basically a register just stores some data. It stores 8 bits of data. In this case, this is an 8-bit computer. And then it interfaces to the bus. And so to really understand the function of a register, you've got to understand how the bus works within a computer and the importance of the bus in the computer. So most computers are organized around a bus, and in fact many computers have multiple buses, but in this case we're going to keep things simple. We have a single bus here. And a bus is basically just a collection of wires that are sort of a common connection point for multiple components within the computer. In this case, we've got an 8-bit bus, so there are 8 wires that we're essentially using for common connection going to all of the different components. And we're building it with the kind of terminal strips for the power from the breadboards. And so what you can do is you can take one of these breadboards and you just snap off this power strip here, and there's some foam tape or something. You can get a knife and just kind of cut that off. But what you end up with is you just end up with these little terminal strips, and you can get a couple of them and connect them together. And that's essentially what I've done here with this bus, is taken 8 of these, and 4 of them at a time here. So you get 4 of these and you connect them together. Each one has 2 strips, and all of the connection points along each of these strips are all connected together all the way down. And so there's 8 lines across here. And then I've got 4 of them here, and then 4 of them down here, and you can see these jumpers here connect them, so they connect all the way down. And that forms the bus, and that forms this common connection point with 8 bits of data that everything connects to. And so all of these blue wires that you see here are connecting, these blue wires coming in from register A, and these blue wires coming in here. This is the memory address register. You can see wires coming in here, from here. All these blue wires that you see going off to all these other pieces of the computer, those are all connecting to the bus. And the bus provides this common connection point where you can essentially do what's called bus transfers, which is moving data from one part of the computer to another, where one module can put data onto the bus, and then another module can read that data from the bus. And so that's what we typically see, and that's one of the main things that a register is going to do. And so just kind of show an example of this, I've got some stuff programmed here that just kind of moves some data around so we can take a look at it. I will manually advance the clock to kind of get things going. And what you'll see is, data is coming and going from the bus. And right now what's happening is we've got particular data in memory. I just have this 010101 pattern, and you can see that pattern is also on the bus, and that's because the memory module here is putting that data on the bus. It's just driving that, just pushing that same data that's here out these wires here and onto the bus. And so that data, you can see it up here. These are just showing what's on these eight bus lines, but that data is also being fed to all these other modules should they care to read it. And so in this case, the way this is set up right now, and I won't go into the details of how it's all programmed, we'll get into that later, but what's going to happen is on the next clock cycle, the A register, register A here, is going to read whatever's on the bus, which is this, and then it's going to latch that into and store that. So we'll go ahead and hit the next clock cycle here, just a manual clock button. And you see now that data, that 010101 data, is in register A. And so what happened is the memory module over here put that data onto the bus, and then the A register read it from the bus. And so we essentially are able to move that data from one module to another. But it doesn't always have to be from memory to register A. It could be from anything to anywhere. So I'll go forward a couple more cycles here. And now we have a different pattern here in memory. So 011001110. And you see that's now on the bus. Now we can, the way this is programmed, it's going to go into register B. So I'll hit the clock again, and you can see now that pattern, that 011001110 pattern, is in register B. Still transferred through the bus, but instead of going from here to here, it's going from here to here. And that's just a function of which register is reading from the bus at a particular point in time. So each of these registers has some control lines that tell it when to read data from the bus or when to put its data on the bus. So for example, right now, the sum register is putting its data on the bus. So this sum, which is just the sum of these two, if you add them up, so 1 plus 0 is 1, and 0 plus 1 is 1, and 1 plus 1 is 0, carry the 1. So this is you kind of add them up. This is the sum of A and B, and so this is the data that's on the bus right now. And what's going to happen on the next clock cycle is that's actually going to go into register A, and there it is. So this was in the sum register, now it's in register A. Of course, sum register is different because A and B are different, but that's not, you can kind of ignore that. But the point is that we can use this bus as this common way of transferring data from one part of the computer to another, whether it's from memory to a register, from one register to another register, or from a register to memory, or register to the output. The bus provides this kind of any-to-any connection, that everything is connected to it, and so we can move data from anywhere to anywhere. Very flexible. To get a better sense of how this works, I've kind of drawn this up to make it a little, maybe a little bit simpler to understand. So this is our bus. We've got these 8 connections, and I've just done each a different color, just so you can see that each color is a separate wire, and this red that you see here going into A is the same red that's going into C. So any voltage that's on this wire is going to show up here, it's going to show up here, it's going to show up down here, it's going to show up over here, it's going to show up everywhere. Everywhere you see red, that's going to be the voltage. But there's 8 of them, so there's eight bits. Each one can be different, but basically all 8 of those bits are showing up on each module in the computer. And this is really flexible because in this diagram I've got A, B, C, and D, but you could have, this could keep going. You could have arbitrarily many modules, and that's what makes this really flexible, because in larger computer designs, there might be a lot of things connected to this bus, and everything that's connected to the bus can talk to potentially everything else connected to the bus. So it's very flexible. But the way it works is each of these things that's connected to the bus, essentially, we can think of them as just as registers, but there's other things that might be connected to the bus, memory and outputs and inputs and so forth. But everything that's connected to the bus, can have its input connected to the bus, and it can also have its output connected to the bus. And in order to control, what's going on the bus, each module also has a couple signals, control lines coming into it. So there's, typically something like a load signal and an enable signal for each. And what the enable signal does is it says whatever value is in this register or this module or whatever 8 bits of data that it has, when the enable goes high, it says put that data out here on the bus, output that data. And so then that data gets output on the bus when this enable goes high, and all of the other modules can then see that data and may or may not do anything with it, but that data goes out to everything else. And then another module, if you turn on this load, if this load signal goes high, that says read whatever's on the bus. So if A sets the enable signal high and C over here sets its load signal high, or C isn't setting it high, but some controller that we'll assume something is controlling these little control lines here. And for now, I'm just going to ask you to kind of take it on faith that is magically happening. In future videos, we'll talk about how that control logic actually works. But for now, let's say that somehow the computer knows that it should turn on the enable of A and the load of C, and what that's going to do is it's going to say A should be outputting data and C should be inputting data, and that essentially causes a bus transfer of whatever data is in A to go over to C. And the actual timing of that is based on this clock input. So each of these modules has a clock input, and there's a common clock signal that's coming in that's connected to all of these modules. Well, each of these modules has a little clock input, and on each clock pulse, whichever modules have their load signal turned on will read whatever's on the bus and load it at that particular time. Yeah, so one thing that's really important about a bus like this is we've got to make sure that...
All right, cool. Next video watched. Everybody kind of understood the usage of a bus and how it interacts with the different modules and the registers. I think that's a very simple thing, I think, to understand. But it's also very crucial to understand the overall design later, and how you are able to learn and understand how the whole setup works. So just want to make sure that whoever is interested in understanding this paid attention to, maybe you need, if you didn't pay attention, maybe rewatch it again or something. Conceptually, yes, technically sort of good enough for me. I'm sure we are on the same page or level here. In the end, it's like shared wires that different modules can interact at different times. I think we will bit technically more understand it once we see how the modules are selected, like why did the register read exactly at that moment, and why did the memory module put these values there at what moment. How is that decided? I think once you learn that, it becomes more clear how it works. But the most important thing is we have this central bus that carries all the different values. I wonder actually what the next steps are. Should we build like the bus and stuff like that? How are they still constructing outside? It's 8:30. Where are my conservative Germans that complain about the noise in the evening? All right. Sorry. Also, I want to help you, but I probably also don't understand it to a level to answer your questions. Well, I don't want actually any noise complaints. I intend to also stream in the middle of the night at some point. So far, my neighbor has never complained me staying up and recording videos and stuff like this. So I hope no neighbor would ever complain when I also stream at night at some point. But it's still kind of surprising how late they are still working on the street there. Anyway, unrelated. I guess let's watch the next video. This stream is really unentertaining. Not entertaining. No. Sorry, what's the term? Not a lot of interaction, not a lot of building going on, but I'm sure soon we will just sit there again stripping wires. Theoretical about the resistors, you mean? Mhm. If you are referring to the resistor stuff I just said, you can put soundproof panels. No way. No way. The whole building is shaking. No way I could soundproof that. Also, this is a complete window front here, so I don't like. It's not something easy to soundproof without replacing the whole window front with different kinds of windows and stuff like that. That's a trick. He just wants to stretch time until his wire stripper is shipped. Yeah. Oh my gosh. Okay, wait. That's another thing I need to tell you really quick. So, if you live in Germany and you have Amazon or even Amazon Prime, the delivery is so fast. Like, I'm so used to next day delivery of anything I order on Amazon, especially because I live in a big city, so everything is usually here the next day. It's it's 95% sure that it will arrive the next day. However, for this year, the wire stripper I ordered with my Amazon business account that is registered to the company, that is dealing with the income of like my YouTube and stuff like that, because it's a business expense for me. I just buy it for the stream, and so I decided to not buy it privately, but through the Amazon business account, and that service is garbage. I've ordered this on Friday, I think. The wire strip I ordered on. I guess I ordered it on Monday probably. But there are things that I ordered on Friday even and stuff, and they just got shipped today. What is this? That's not what I'm used to from Amazon. It's really. I'm too spoiled. Okay. Sorry. Okay, let's watch the next video.
Only one of these things that's connected to the bus is outputting something at any point in time. Because if for example, both of these modules are outputting to the bus at the same time, then we're going to have some sort of problem here. If for example on this blue bit here, if A is outputting a 0 and C here is outputting a 1, then we're getting a 1 and a 0 both output onto the same line at the same time, and then it's not clear what the inputs are going to be. So to really understand better, what's happening when we have all of these outputs connected, essentially together in this way, it's useful to look at the actual output stage of a gate, because ultimately these connections are coming out of logic gates, right? Because whatever's going on inside here is just a bunch of logic gates. So if we were to look inside a typical logic gate, there would be some series of transistors and things that kind of do whatever logic operation that the logic gate is supposed to do, whether it's the AND gate or whatever. But then there's typically an output stage that looks something like this in front of the actual output of a logic gate. And usually there's these two transistors, and if this top transistor is turned on, then current can flow from the voltage source through and to the output, and so essentially the gate can be sourcing current, that goes out the output, and that's typically what it does when the output is a 1 or when the output is on. Alternatively, this transistor could be off and this transistor here could be on, and you can think of it as connecting the output to ground, or you can think of it as the output is able to sink current, and that's represents sort of the 0 state of the output. So another way to look at that is like this, where when the gate is on, there's this resistor that essentially connects you to the output. So sort of a resistor goes to the output, and then on the input here, what that means is that current can flow out of this output and then to ground in the next gate, and so current flowing in this direction is seen as a 1. Alternatively, if the bottom transistor is turned on, then we have this scenario here where current can be sunk essentially into that output to ground. And when current is flowing this way, we consider that a 0. So if we come back to this bus, essentially when these outputs, if A is outputting some pattern, 0, 1, 0, 1, 0, 1, for example, really what it's doing is it's saying, okay, this pin is going to sink current, this pin is going to source current, this pin is going to sink current, this is going to source current. And so, on an input, you're going to see current going one way or the other, and that's how the input is going to determine whether it's a 1 or a 0. And so essentially current will be flowing this way, or current will be flowing this way. And that's fine until you have, two things trying to output at the same time. So if for example you said, okay, well, C is not going to output anything, so it'll set all these to 0. Well, that's no good, because what that means, if you're setting all of these to 0, that means that it's going to sink current. And so if you have a 1 here, you're actually going to get current flowing out here and into the output here. That's not really what you want. You really want these to be essentially disconnected. And so there is a way to do that, where this gate, rather than turning on this transistor to output a 1 or this transistor to output a 0, if you don't turn on either transistor, then the output is not going to source current or sink current. And so essentially you're not going to get a 0 or a 1. You're just going to kind of have this output disconnected almost. And if you didn't understand anything that I just said in terms of sourcing or sinking current, that's okay. A better way, or maybe a simpler way, or a sufficient way to think of this is you can think of a gate in this way. So instead of thinking in terms of what transistors are turning on and off, if you think of it like this, where you have an input coming in, and this is just a simple buffer, whatever the input is, the output's going to be. The input you can think of as just controlling a switch. And so if the input is a 1, then the switch is up in this position and you get 5 volts coming out. If the input's a 0, then the switch is down in this position and you have essentially your output connected to ground. So you could sink current, or you can just think of it as the output is at 0 volts. But what we could do is to sort of, as an easier way to think of this scenario where both of these transistors are off, we could think of having an enable input. And if this enable input is a 1, then it kind of closes this switch. It connects the output. And if the enable input is a 0, or if it's off, then we can think of this switch as being open, and we can think of the output as being completely disconnected. And that's what we want, is we want these outputs, if this particular register is not enabled, we want those outputs to be disconnected. We don't want them impacting, some other data that's being transferred on the bus. And so, fortunately, they make gates like this. They're called tri-state gates, or typically called tri-state gates, because they have 3 output states. There's a 0 or a 1 or a disabled, or a sort of a not connected. Sometimes you'll see it referred to as high impedance or high Z or something like that. But basically this is considered a 3-state gate. And this is a pretty common symbol for such a thing. You have an input, and this is a buffer, just an input and an output, but then you have this enable coming in the side here. And so an example of this that we'll use in our registers is the 74LS245. And you can see it's got a bunch of these gates in here, but what you should notice here is you can see you have an input that comes in, and then you have an output that goes out, just like any buffer. But you have this third enable pin, and it goes over here. And there's a little bit of logic here, but essentially you have an enable input. That's this E input that enables this thing. And so by using this tri-state logic, it gets us essentially what we want. It gets us the ability to have this enable line for each of these modules that's connected to our bus, and we can have that enable line low for all but one of these. And as long as it's low for all of them except for one of them, as long as only one of them is enabled, then there's only one thing that's going to be outputting either 0s or 1s to our bus. And so we won't have any conflicts on the bus. And then when some other module then reads the data on the bus, you're going to be getting the data from the one module that's outputting that data to the bus. So I know that's a ton of theory, and it's okay if you didn't catch all of it. But the important part here is this notion of a bus and how that works, and how that gives us the flexibility to add lots and lots of different modules, and how when modules are connected to a bus like this, any module can talk to any other module. And then as we start to look in the next videos to build one of these registers, and a register is just going to be able to store data that comes in and be able to put that data back on the bus. It's important just to understand how this works, and understand that, okay, this thing is going to connect to a bus. It's going to have data could be coming from the bus, or data could be going to the bus, either way. And that's controlled by these control pins that come in, or these control lines that are going to come in from somewhere. We haven't talked about where those come from, or how the computer knows when to turn those on and off. And so if that's a little bit of a mystery to you, that's fine. We'll get there. But essentially, we have an enable control line that says whenever that enable is high, then the data that's stored in here should be output to the bus. And of course, we have to make sure that only one of those enables is high at any point in time. But we'll get to that later. And then there's also a load signal, and when that load line goes high, then what that means is that on the next clock pulse, we have a clock input here, on the next clock pulse, it should read whatever's on the bus and then store that in the register. And so in the next video, we'll actually look in more detail about what goes on inside this register and how to build one. So in the last video, we looked at...
All right, okay, cool. So here's something that I'm really excited to learn about. He explained it already, but I didn't quite get it yet. But I'm sure I will understand it once we build it. I have always been wondering about this with the different components reading and writing onto or with the bus, because of like this idea of like short circuits, or like what if two things would want to write to the, like what would that, how would that actually look like? So he explained that with the tri-state. I've been always kind of wondering about how that works, and now kind of understanding like the purpose of this bus chip and stuff like this. I'm still not quite 100% comfortable with it. I couldn't like explain it to you now, but I have a feeling of, I have an intuition of how it works. So I'm excited about that. Looking forward to then actually build that. How's it going? What modules have you been able to build? So far we have only built the clock module, as you can see here. Today is the 4th stream, I think. So we spent 3 streams building this, as you can see. And now we just watch the next couple of videos where they are a bit more theoretical, explaining flip-flops and stuff like this. And I guess, as Ben mentioned it in this video, that we will now next look into how to build such a register module. So I guess this will be the next building plan. Yeah, this series is amazing. Yeah, the series by Ben Eder is awesome. This is great. It's kind of long. If you just like watch it, it might be a bit dry or something like this, but it's really a gem. It's if you're interested in how a computer kind of works, it's really awesome, and building it is super fun. So I'm super excited about it. Yeah. All right. I'm a bit worried about the next video and building the module, because I've already streamed for 1.5 hours again. Not doing it would mean we didn't do anything in this stream. That would kind of suck. And tackling the next thing, then I kind of want to get it to a finished state, and I worry that will then take us too long. So not quite sure how to deal with that. But I guess I need to at least start watching the next video, and let's see how... Oh, that one is also 20 minutes long. Okay. I try to stay more towards 2 hours than over 3 hours. So, or let's say under 3 hours is my goal. But I definitely need a mate now. I'm so tired. So maybe you can watch a little bit the lights blinking for 30 seconds until I'm back with my mate. Oh, but I could also, just for fun, get it to roughly 30 FPS, just a little bit higher or lower. And then you get a nice pulsing light that you can. Awesome, look, that looks cool. So that is they are running now with close to 30 FPS or 30 hertz. Okay, be right back, 1 second. Okay, I'm back. Good old Club Mate. That's the mate choice for me. The problem with Club Mate is that you can only buy it in Edeka markets. That's a bit easier where I live, but I also order from Bringmeister, which is Edeka. Is Bringmeister Edeka stuff? I don't know. Also, the dog just joined me here. The dog just joined me. Come, do you wanna say hi to the stream? Yeah, he's very excited to be carried up and sitting on my lap. Oh, wait, I need to make the screen larger for you. There we go. Yeah, isn't that a cutie? Do you like that scratch? You like that scratch? Okay, I let you down again. There we go. That's Mr. Doggy. Okay, let's head into the next video. Hi. So you are from the south of Germany, I assume, if that's what BW means. Okay. I'm way too tired to just be watching videos. Oh, god damn it, I want to strip some wires. Okay, let's do it.
At the concept of a bus and how we can use a bus, which is this set of 8 wires, in this case 8 wires, connecting multiple different modules together, and how the bus provides a way for any module to communicate with any other module. So in this video, what I want to look at is actually what it takes to build one of these registers. In this case, we'll look at a register. These could be other things, could be input or output, but we'll look at building a register. And so a register, basically, what we're trying to build is something that has 8 inputs connecting to our bus that can store a value. So there's some 8-bit value stored in here, series of 1s and 0s, and it's connected and it can send that value out to the bus when the enable input is high. So there's an enable and a load control input here, and normally the enable input would be low, and so whatever value is stored in here is not going to be output to the bus. So it could be some series of 0s and 1s, and we're not going to be outputting a 0 or a 1. We're essentially going to be disconnected. essentially, because we're not outputting a 0 in the sense that we're not sinking current, and we're not outputting 1s in the sense that we're not sourcing current. We're essentially just appearing to be disconnected from the bus. So if we're not enabled, other modules can communicate, and this module here is not going to interfere. But when this enable line does go high, then whatever value, whatever series of 1s and 0s are stored in this register will be output on the bus. And any of these modules on their inputs should see that same series of 1s and 0s and could choose to load that value into their own storage. So this register here, for example, has this load input. And if normally that load input would be low, but when it goes high, then what happens is this module here is going to latch whatever value it sees on the bus. It'll store that. And it uses a clock input to do that, so we can coordinate the timing. And what happens is, once that load input goes high, then the next time the clock transitions from low to high on that rising edge, then whatever value is on the bus gets stored in C. And then the load input can go low, and other things can happen on the bus, doesn't matter. We've now have that value stored in C, and so we've essentially transferred the value from A to C. And so A can take on another value, other things can happen on the bus. C is going to remember that value. And then it can be enabled, and it can put that value back on the bus at a later time, or whatever needs to be done. So what we're looking to do is we're looking to build something that can store a value when on the clock rising edge, only when the load is enabled, and then hold on to that value and then output it to the bus whenever the enable input goes high. So if you've watched my videos on the D flip-flop, you might think, well, that's a pretty good candidate for something to use. And if you haven't watched my videos on a D flip-flop, I would suggest going back and taking a look at those if you don't already have some idea of how a D flip-flop works. But just as a reminder, the D flip-flop has a D input, and it also has a clock input, and it uses this edge detection so that on the rising edge of that clock, when that clock transitions from low to high, at that instant that it transitions from low to high, it stores whatever value is coming in the D input, whether it's a 0 or a 1, it stores it in the latch, and then that output is available at the Q output. So you might think, well, we can use just a series of these D flip-flops to build a register. So we have, however many we need. We're building an 8-bit computer, so we have 8 of them. And have those inputs, and then just tie all these clocks together, and somehow that might work. Well, the problem with that is we need to have some mechanism to not just always store whatever's coming in, because these D inputs are going to be connected to our bus, and the value on the bus is going to be constantly changing. We only want to store the value on the bus in the register essentially when we're told to, using that load. Remember, we've got the load input, so we only want to load what's on the bus when this load input is high. Otherwise, we want to keep what is in here stored in here. So what we can do is add a little bit of extra logic around our D flip-flops to kind of control how the clocking is worked. So we still have our clock coming in here, and this is going to be our master clock for the computer that everything is connected to. That clock is coming in here. But what we have is we have our load input over here. And our load input goes through some logic here that controls whether we actually are loading a new value into the D flip-flop, or whether we're loading the value that is already in it back into it, which is essentially doing nothing. And so normally if this load is low, let's say it's low in this case, then we're going to have it coming in over here. We're going to have a 0 down here, and we're going to have a 1 over here. And so we're looking at this coming in through this AND gate, so we have a 0 and something else. Well, it doesn't really matter what this is. If we have 1 0 coming in here, we know the output's going to be a 0, right? Because if it's 0 and 0, that output's going to be 0. If it's 0 and 1, then the output's still going to be 0. So we know that's a 0. Here, we're inverting that 0, and we get a 1 over here. And so in that case, we know that 1 and 1 is going to be a 1 over here. 1 and 0 is going to be a 0 over here. So whatever this is, we'll call it x, we're going to get the same thing out over here. So this same value is just going to pass through. So this AND gate essentially is going to appear to be transparent. So now we have an OR gate here, so we're saying 0 or whatever x is. Well, that's just going to be whatever x is. So x, that's what's being fed out of the D flip-flop, right? So whatever's stored in the flip-flop is just getting put right back in the input. And so whenever this clock transitions from low to high, the D latch essentially just latches in the same value that it has, and nothing changes. And that's because our load is 0. Now let's imagine a scenario where our load goes to a 1. So we have a high value coming into our load input. So in this case, this second case is the exact same circuit. So I'll just draw it down here so you see what's going on. So this is a 1 now. So we have a 1 here, we have a 0 here, right? We're inverting that. And so now, this value that's coming in here, we'll call it x, whatever that is. It doesn't matter what it is because we're ANDing it with 0, so we know we're going to get a 0, right? So if x is 1, 0 and 1 is still 0. 0 and 0 is 0, doesn't matter. So this is a 0. But down here, we have a 1 and whatever's coming in our input. This is coming in from our bus. So these D1, D2, D3 could keep going for however many bits we have. We have 8 bits, so there's going to be 8 of these things. So that input from the bus is going to come in. So whatever that is, we'll call it y. And if we AND that with a 1, then we just get y coming out. And then of course, if we OR that with a 0, we get y coming out of our OR gate. And so in this case, when our load goes high, when it goes to a 1, then when we get a clock pulse here, instead of storing the same thing that was in the flip-flop, we store the thing that is coming in on the bus. And that's exactly what we want. We want to load, when load is high, we want to load the thing that's on the bus. And then that latches it into this flip-flop, and we've now stored it. And now that new value will be output of this Q output. So this will now be Y. That'll be latched in there. So if we want to, we can go ahead and build this. And this is actually this circuit here is built here. And I've used 4 chips here, and just so you know what they are, I've got this is a 7474 or 74 LS74, and that is basically has 2 D flip-flops built into it. And so this is the data sheet for it, the 74 LS74, and you can see it's got 2 D flip-flops built into it, and we're using this one over here that's sort of these pins on the bottom. And so you can see it has the D input here. You can see it has a clock that goes over here to the clock input. You can see it has the Q output over here. And it has our inverted Q here as well. And it also has a couple other nice things. It has a clear pin, so regardless of the clock input and everything else, you can, if you take this clear pin low, then it just resets the flip-flop, it resets it to 0, sort of regardless of whatever else is going on. It's kind of an override. And then there's also a preset pin, which kind of does the opposite. It sets the flip-flop to 1. So we're not going to use those necessarily, but that's what those extra pins are. So we've got that here. This is the 7474. And of course you could, in the previous video, I built a D flip-flop from discrete logic gates, and we could do that if we wanted to. But in this case, since I've already got those videos, hopefully you can watch those and know how this works inside. So we're going to take a shortcut and just use that here. And then I've got an inverter. This is a 74LS04 inverter. I've got some AND gates. This is a 74LS08. It's got 4 AND gates on it. We're using 2 of them here. And then the 74LS32, which is the OR gate. And so we're using 1 inverter. We're using 2 AND gates. We're using an OR gate. And we're using, in this case, I just have one of the 74LS74, one of the D flip-flops on this chip wired up. And so what's going on here is we've got our load input. That's this yellow wire here. And so we have that load input going into one AND gate. And then we have the inverted version of that load input going into the other AND gate. And so the one AND gate that's going into the other input of that is our connection to our bus. This is our data input here. And so that's going into the same AND gate as the non-inverted load. So you can see that is going into the same AND gate here. And then the output of that AND gate, this third pin, is the output of the AND gate. That goes over to one of the inputs of our OR gate. Right, and that comes over to one of the inputs of the OR gate. The inverted load is this, comes out of the second pin of our inverter. And that goes over into the other AND gate here. That's right here. And then the input, the other input of that is this green wire here at the top that is coming from the output of our flip-flop, the Q pin, I guess, of our flip-flop. And we also have the LED hooked up to the output there, so we can see what the output is. And so the output of that other AND gate is here. That's this pin, and that is going over to the second input of our OR gate. So our OR gate's got both of our AND gates connected to it. Those are these two wires here are the outputs of the two AND gates going into the two inputs of the OR gate, and then the output of the OR gate comes over here to the D input of our flip-flop. And then this white wire here is just the clock for the flip-flop. So we'll hook that up to a clock here. And then, of course, the output over here I mentioned before, we've got the LED hook there so we can see what it is. And, of course, it's also going back around to our input here. That's this longer green wire. So we can hook this up and see what happens. And it looks like it appears to be nothing, but I guess there's a 0 stored here in our register, I guess. This is a 1-bit register, I suppose. So what we can do is we can set our load to low, and then our input, we can set that as a low or high. Let's set it to high. So we can see that right now, the bus can be low, high. It doesn't really matter. The state of our register doesn't change. And then our clock input we can hook to a clock, and conveniently we built one of those in previous video. So I'm going to hook this clock that we built up here, so just connecting the power across here. So now our clock is powered, and so we can manually advance our clock, or we can turn this on and we get a nice slow clock. And so I'll hook our clock up there. Okay, so we've got our clock hooked up, we've got our input, and so now our input can be high or low, and actually I'll let the clock run. So when it's low, you see nothing's changing. When it's high, nothing's changing, and that's because we haven't enabled it. So if we've got it high now, and we enable it, we see that with the clock rising edge, it stores that 1. And now if we disable it, the bus is free to change to a 0, to a 1. It doesn't matter, we've now stored that 1 in here, in our register. And now, the bus is a 0. Again, if we enable, or if we load, I should say, this is our load input. If our load input goes high, you see it stores that 1 that's on the bus. And of course now if the bus is changing, it's going to pick up that new value because we still have our load high. But normally the load is going to go high just for 1 clock cycle, or 1 clock, I should say. So this appears to be working. It seems to be doing everything that we need our register to do, with one exception, which is that we have our output here, but of course, one other thing that we need our register to do is not always send its output back, right? So if we just hooked the output of this back to the bus, we'd be constantly forcing the bus to either be a 0 or a 1, whatever this register is set to. So we'd like to add a tri-state buffer or something here, so that we can use that tri-state function of the buffer to turn off the connection to the bus. And so the chip that I'd like to use for that is the 74LS245. And you can see it's got a bunch of these tri-state buffers. So there's a lot going on in here. I know it's a little bit complex, but if we just kind of look at, if we just look at this side here, what you'll see is we have an input here coming in on pin 9, and it's connected to a tri-state buffer that then has its output connected to pin 11. And so you can see we can use this tri-state buffer to sort of connect and disconnect data flowing in this direction. You notice there's also a buffer flowing in the other direction, which can be convenient for connecting to a bus, and that's why this chip is considered a bus transceiver. It is useful for interfacing with a bus and sending data in both directions. And there's a pin 1 here is a direction control, and you can see that it's hooked up to a couple gates here that essentially control, whether the bottom row of tri-state buffers is on, in other words, data is going this direction, or whether the top row is on and data is going this direction. In our case, we only want data to flow in one direction because we've already got the load function here worked out. So we really just need the tri-state buffer on the output. And so for that, we can essentially just tie this direction input to high value, to 5 volts, and that'll force it to always go this direction. And then we have an enable pin here that we can just use to turn on or turn off all of these all at once. So this is a good chip to use as our buffer. So we could add this to our circuit here that we have. And then of course we would need to essentially build 8 copies of this. And there's room on some of these chips, but it would still take a fair amount of room to do that. And so this is where we kind of come to we have a decision to make, I guess, which is what is it that we're trying to build here? Or what is it we're trying to do? I mean, we could approach this and say, our goal is to build a computer using only basic logic gates. And maybe we want to build our register using this. In fact, maybe we don't even want to use the 74 LS74 as our D flip-flop, and we actually want to build a D flip-flop from AND gates and OR gates, like we have in previous videos. And that could be a goal. You could choose to build a computer that is just AND gates and OR gates and inverters and that sort of thing. My goal with this, I think, is more to learn a bit about building the computer and how the computer works, and have a project that you can do kind of in your spare time over a couple of weeks, and not be so hardcore that we only are going to use AND gates and that sort of thing. And so actually, what I'm gonna do for the registers is actually something even simpler than this. Which is the 74LS173 is a chip that is a 4-bit D-type register. And so it is actually designed to be used as a register. And so what you'll see here is you'll see that this 74LS173 has 4, doesn't quite fit here, but it's got 4 D flip-flops in it. And it has this same logic that we've been looking at. It has the output coming back around into an AND gate, and then 2 AND gates going into our inverter. And you can see the input is going into the other AND gate. And then you can see the other sides of these AND gates are connected to either side of an inverter that goes to our, they're calling it the enable. This is sort of our load inputs. And it's a little bit weird. They have 2 of them and they're inverted. I'm not really sure why they did that. It's a little bit less convenient for what we need, but definitely more convenient that all of this is built into one chip. So I'm gonna use this chip. And the other nice thing about this, sort of nice maybe, is it also has tri-state outputs, and it has an output control. And again, they have 2 of them and they're inverted. I'm not really sure why, but they have this output control that we can use to turn on or turn off this output. So you do have a choice of whether you want to use the 74LS173, which gives you a lot of the functionality in one chip, or whether you want to, kind of go extreme and try to build it out of discrete logic gates. It's up to you. For my money, I say, use this. I think in the computer that I'm going to build here, we're going to use maybe 10 or 12 of these chips of the 74LS173s. And so if you were trying to implement that with discrete gates, I mean, you could do it, and maybe, I don't know, maybe you enjoy that challenge. But I think there's enough other challenge in building this computer that I think it's perfectly fine to take a little shortcut and use a pre-built register like this. So in the next video, we'll go ahead and use the 74LS173s and build a couple of the registers that we're going to use for the computer and go through testing them.
Yeah, it sounds good.
So in the last video, we
And using an IC, what a casual. We should be building it out of transistors and resistors. But yeah, there's some kind of beauty in it to just use transistors. Then it would be even larger. What wasn't this one? What is it called? We had it on stream the other day. This one PC that is like built around like a whole room on the walls. I think that one is using only transistors if I remember correctly. But yeah, it would also be kind of cool to just use the transistors themselves. But yeah, I mean, for an educational reason, as Ben Eater says, it's, now we understood how it works. Ben Eater has shown it, has demonstrated how these things actually work, that they are made of, and in the end we use finished chips. Mega processor, right. I think that was the one. Yes, it's close to only using transistors. You would need a lot even if you use mask to simplify as much as possible. Yeah, for sure. Yeah, of course. Alright. Oh man. 2 hours into the stream and we haven't built anything. Feels bad. But I hope that soon now it feels like a lot of basics are covered, and now we building the ALU. There's only I think after that was the driest, most theoretical parts. I think it seems like that afterwards most of the stuff is building and testing. Yeah. Cool. Oh, hey, Pro GJ. It's going well. Today's stream is very boring and dry because we have only been watching some theoretical kind of videos. We haven't continued building anything yet. So the next video is building the 8-bit register. So we are at 2 hours. Let's see, I want to stay under 3 hours today. Maybe, I guess this video is only 9 minutes. I guess we can start and then maybe start building the register. In the worst case, we will not finish it today and do it tomorrow. Did you try using logic simulation? I don't know is that a tool? Like the video. I'm not logged in here. I can't I need to sign in. I also can't subscribe. Were there any other questions? Oh yeah, I forgot. I've not seen a streamer fall asleep on stream before. There have been plenty of streamers falling asleep before. I have a real problem with just getting one sensory input that makes me really tired. It's really weird. I can so easily fall asleep in front of the computer sitting in my office chair, but once I get ready for bed and lay in bed, I can't sleep. I just lay there and toss and turn. But sleeping on my office chair, no problem at all. But yeah, I'm a bit tired today. I didn't sleep too long today. Got up very early. Yeah. Did you buy all the parts at once for the build, or did you have some already? Of course, I have some parts already, but I ordered everything I needed. Ben Eater has a parts list on his website, and I just ordered everything that I could find from various German stores. So I have it here. However, I plan to do a second order soon. I just want to collect a few more things that I definitely need. For example, the potentiometer that we are using here is kind of shit. It's super huge, as you can see. And this switch here to switch between the manual mode and the automatic clock mode is, I don't know, not the best kind of switch. It's a bit too stiff for the use of just being stuck here into the breadboard. It always has a feeling of ripping it out or something. But yeah, and then maybe I want to order some, for example, and then we want to upgrade this at some point later too. Maybe adding more registers, for example. I think the basic design from Ben Eater, for example, doesn't have a stack pointer. If you want to implement something as a stack as well, for example, like a typical CPU you might know, then you might want to add another register as a stack pointer register or something like this. So maybe we need more chips like that. But I think I have a better idea of what maybe the kind of parts I need once we are a couple of more videos in, and I kind of start to understand better what the modules are for and how it works, and then I might do another order. Can you share how much you spent? Yeah, it was, I think, 240 euros. The most expensive parts are the breadboards. You could find cheaper breadboards. For example, Toby said he ordered some on AliExpress. I'm sure he paid like just a fraction of what I paid for that. I bought exactly the breadboards Ben Ida was using, mostly because I happened to watch, like I was looking around YouTube what other people were building based on this series, and one person was kind of telling their experience they had building it, and they said that they were using cheaper breadboards and they had like connectivity issues and just kind of like issues with cheap breadboards. And so this person in the video was referring to that Ben Ida was using high quality breadboards. So I decided, oh, I really just don't want to like be annoyed by that. If that breadboard is really good quality, then let me buy the same one Ben Ida used. And so that was a little bit more expensive, I guess. I think you could build a register in about 30 to 40 minutes. Yeah, okay, then let's start the next video and get going. I wonder, do you run the streaming from your PC or from your MacBook? The streaming setup right now looks that way, that I stream from my Windows machine over here. That one has the main OBS with all the scenes and Streamlabs and everything set up. This is where the cameras are connected to. And then I have the laptop here. This is the screen you are seeing right now. So this is this laptop here. And there is this plugin for OBS called NDI, I think. You can see it here in the tools. It's called NDI output here. And basically that just streams the whatever OBS is recording on this machine here is streamed over the network to anything that wants to pick that up. And so this streaming PC has an NDI source video configured and just picks it up and includes it into the scene in OBS. So that's the current setup, which I actually quite like a lot. This machine, you know, has much stronger CPU and also GPU. I don't know if it's necessary, but I feel very comfortable streaming from that machine. But at the same time, I can have a clean laptop that shouldn't leak anything accidentally that I then use to browse the internet and stuff like that. So that seems like a good setup. Why not from China? It's cheaper. Yeah, that's what I meant. Like you can get cheaper breadboards, but I don't know. You know, it's a fun project for me. I don't need to worry about the last euro. I mean, overall it was 240 euros. You know, this oscilloscope costs more. These headphones cost more. This attachment up here is half. Like for this camera here is half of that price what these parts cost. You know, this is my hobby. I like to spend money, so 240 euros is, you know, absolutely in the range of what I like to spend for it. I mean, if it would have been like 500 euros or so, you know, double that, then I would have thought twice and I might have chosen cheaper breadboards, but that was fine. Honestly, it's just memory and a register and a tiny bit of logic. Probably not hard to do once you get a computer built. Yeah, okay, well, yeah, then we definitely tackle the next one. Let me just quickly read over chat, and then we tackle the next part. Nice. Nice streaming setup. Separating the streaming PC from the recorded PC is a good idea. Yeah, I always wanted to do that. However, maybe when I want to do some gaming streams, you know, like transition into gaming, then I obviously want to play on that PC, so I don't know how to do that. Yeah, I'm live. You also, I guess, joined at a better time because we watched a lot of videos and didn't do anything. But now with the next video, after watching next video, we should continue building actually. All right. Okay, then let's just start watching the next part and not procrastinate too much.
We took a look at building registers, and we actually built a register, well, a 1-bit register anyway, using somewhat discrete logic here. We did use a D flip-flop. But then I also talked about the 74LS173, which is basically a 4-bit register on a chip, and how we were going to use that. One thing that I don't like about using just the 74LS173 is that it does have its own output control, which means that once it stores some series of bits here in these latches or these flip-flops, you can't see what is in it. And I think it's pretty important for this computer, because this computer is designed as something that you can use to learn about how computers operate. And I think it's pretty important to be able to see what's in every register. So what I'm going to do is I'm going to use the 74LS173 register chip, but I'm going to tie the output control such that the output is always on. But of course you don't want the output to always be on, otherwise the output will always be outputting something to the bus. And you don't want that, because then that register is putting its data on the bus all the time, and that defeats the purpose. You want to have that enable ability. And so what I'm going to do is I'm going to have the output always on, so that we can hook LEDs up to this output. But then on the other side of those LEDs, I'm going to use something like the 74LS245, which has these tri-state buffers in it. That way we can use the 74LS245 to control what's going out on the bus. So have the 74LS173 register always on, so we can see the LEDs to tell us what's in the register, but then use this to control whether it's actually being output to the bus or not. So essentially, that kind of looks like this. This is sort of what that circuit would look like. Hopefully this makes some sense. But I've got the 74LS173, and each one has 4 bits, a 4-bit register, so I'm using 2 of them to cover our 8 bits. So we have our 8 bits coming in. And then I have the output, so M and N. I'm not sure why they call them that, but those are the output controls, and for some reason there's 2 of them. But in any event, if you tie both of them to ground, then the output will always be on, and so these will always be outputting, which is what we want. And then I have the 8 LEDs hooked up, so we can see what's stored in these registers. So the output's always on, and you can always see on these LEDs what's actually stored in those registers. You can ignore this line. I needed to draw this bigger than I thought. And then we're using the 74LS245 to actually control whether it goes back out on the bus or not. And so there's an enable line that the 74LS245 has, and it's an inverted logic line, so it would normally be high, and then you bring it low to enable it. And then when you bring that low, then we'll see whatever this is will actually get output. But if the enable is high, meaning it's not enabled, then this is essentially shut off, and it's not outputting a 0 or a 1 to the bus. So this is fairly simple. We've got 8 connections to the bus as inputs. We've got 8 connections to the bus over here as outputs. We've got our load signal coming in, which is connected to the 2 load pins on each of the 74LS173s. And again, this is inverse logic, so when you bring it low, that tells these to load the value from the bus. We've got the clock, which I don't think I drew, but the clock would be pin 7 on both of these 74LS173s. So you need to tie pin 7 together and then connect that to your clock. I did draw pin 15 here, which is the clear line, which we're not going to use yet, but eventually, when we get the rest of the computer built, we'll want to tie all these clear lines together so you can have a button somewhere to just clear everything in the computer, which can be helpful. And I think that's pretty much it. Yeah, there's the direction here, which we're just tying to 5 volts so that the direction is always in this direction from this side to this side. So I've started to build this here. So this is these are the two 74LS173s. These are our register chips. And then of course our 245, 74LS245 over here, which we're essentially using as the output buffer. And I've got some LEDs hooked up here, just kind of stuck in here on the outputs. So you can see pin 3, 4, 5, and 6 is connected here. Pin 3, 4, 5, and 6. I've got the LEDs there. Same thing over here. Pins 1 and 2, as you can see here, tied to ground, and that just enables our output all the time. So we'll always see the output on those LEDs. Pin 7, which I didn't draw here, is the clock, and you can see I just tied those together. Pin 7 on both of these with this white wire, and then we'll have to connect that off to our clock, which is going to be elsewhere in the computer. The clear signal is pin 15, so I've just tied the pin 15s of each chip together. And then our load here is pins 9 and 10 on both chips. And so you can see 9 and 10 tied together. So those are just all tied together, and then we'll just need to connect our load signal to here somewhere. So now all that's left to hook up here is connecting the outputs of the 74LS173s, which of course are already connected to these LEDs, which are just connected across to ground. I don't know if you can see that here, but they're just connected across here to ground. And we just need to connect those as well to our 74LS245, so just connecting these across. And conveniently, all of these pins are on the same side here. So 1, 2, 3, and 4 are kind of on the bottom side of this chip here, and the inputs for the 74LS245 are 2, 3, 4, 5, 6, 7, 8, 9, and those are all down here on the bottom of this chip. And actually, one of the reasons I'm using the 245 specifically is because of that. It just makes the wiring easier, because you can set the direction as one direction or the other. So you might wonder, if you're wondering why we're using this bidirectional chip, but then only using it in one direction, it's actually just because it makes the wiring easier, and it doesn't cost any more than any of the other chips. So I'm just going to go ahead and hook this up. You just have to be careful to squeeze all this in here. It can be a bit of a tight squeeze. And of course, you are under no obligation to make your board look as pretty as mine. I'm just trying to make this easy for you guys to see what's going on. But certainly no one is going to hold it against you if you've got a big old tangled mess of wires. And now I'm starting to cover up this black wire under here, which is why I wanted to show you everything else before I stuck the rest of this in here, because it does kind of mask what's going on underneath. But there we go. We've got this hooked up now, so that all of our outputs here from the 74LS173 register chips are hooked to the 8 inputs across our 74.
Oh, hey, Zoding, thanks for the raid, and welcome everybody, or for the host, thanks so much. Zoding is streaming a lot of development, so everybody who has been here right now and hasn't heard of Zoding, definitely check him out and leave a follow there as well. We continue working on our 8-bit computer, following the series of Ben Eder, of building a computer on like breadboards. Today was a very theoretical and kind of not necessarily boring, but we didn't really build anything yet. We had to learn about some basics first, but now we watched a video where it is explained how to build a register module that will later be part of the CPU that we are building. So this will be one register, and we are almost finished with that video, and then we can start building. So if you hang out for like 3 more minutes, then this video is done and we start building again. Then the stream will be a bit more interactive. So let me continue really quick.
74LS245, which is over here. So the other thing we can do, or that we should do, is tie the bus sort of terminals here together, right? So each of these 74LS173s has 4 connections to the bus, and so across both of them there's 8 connections to the bus. And then the 74LS245 buffer here also has 8 connections to the bus. And we can actually just tie those together directly here, and then coming off of this board, we'll just have one set of connections. And it might feel kind of weird to tie your outputs back to your inputs, but remember, we've got our load and our enable signals, and we're only going to be doing one or the other, right? So really, this is only sometimes an output, and this is only sometimes an input. And if we're doing things right, they're never an input and an output at the same time. So connecting them to each other, it might seem strange to connect the input to the output, but it's actually okay. Okay, and that's pretty much it. And so the connection to our bus is these eight blue wires, or sort of this side up here. So we want to just add these connections here that we can connect to a bus. Let's do that. And so these 8 wires here are our connection to our bus. So we've got our load signal over here. We've got the enable over here, which is the enable for the output to the bus. And of course we've got the reset here as well, which is this pin 15, which we'll just tie that to ground. We're not going to use that. We'll just leave that so that it's not resetting everything. And then the last thing we have is the clock, which is right here. This white wire connecting here. And so that's it. That's pretty much our register. So register.
Awesome. Okay, cool. So that's the register that we want to build now as well. Like that for now. Yeah, that looks cool. It's electronics, 8-bit computer. I'm sold. Yeah, so my background is mostly in software. I'm an amateur in electronics, but I want to do this project to learn myself as well, learn a bit more and understand better how a computer works. And so in this series by Ben Eder, feel free to watch the series not on stream, just by yourself. It's amazing if you wanna understand how a computer kind of works to the lowest level. So yeah, I think this is a real fun thing to do on stream, and I want to learn, so I think it's cool. Yeah, you are new. Welcome. Oh, thanks for liking my YouTube videos. You work on Docker for Windows? Like you work at the Docker organization, or what you do? What are you up to? Okay, cool. So let me get the breadboards from over here. Look at these breadboards. I guess like that. I thought I had an open. So, in case you were wondering, the brand of these breadboards, but you can also find them on Ben Eder's parts list. These are the ones that Ben Eder was using. They are from BPS Busboard Prototype Systems. How many breadboards do you have? So the part list from Ben Eder requires 14, and I bought 16. I bought basically of everything that I bought, just like 1 or 2 things more depending on the price. And I figured if the whole thing needs 14, and having 2 more in case you want to play around or something like this, or maybe one has an issue or so. Is the register made with D latches? With D flip-flops kind of. So we are, we watched the video just right now. Basically Ben Eder, if you look here at the playlist of videos. So he started by explaining an SR latch, then a D latch, then a D flip-flop, and then talking about how you can design a bus and a basic register. So he's explaining like and then what three-state logic is for input and output on a bus. And then after that, he builds like a 1-bit register based on a D flip-flop with some other circuits for this three-state logic for the bus, basically. And then he explained, like this 1 bit already took up a lot of chips if you do it with the gates yourself. So in the end, now he's using the 173 chip, which is like let's see his parts list again. It's like an integrated register kind of thing. So this is Ben Eater's website. It's eater.net. Eater.net. So registers, I guess. And then schematic. Here, the 173, it's a 4-bit D register, and then now we can have a look again. So it uses inside here these flip-flops, and I think these should be D flip-flops, right? So this is how the chip then looks like. It has a little bit of logic for like enabling and disabling and output control and all that stuff. Now, I was just wondering, because on my chip, it should be fine, right? It says 173AN, not just A. So I wonder if is that a different, or is that the same thing? We want the data sheet. Data sheet. If I would have bought now something else, like an inverted, oh no, it links to the same data sheet. It's the same one. All right, perfect. Latches work when the clock is high constantly, so when the clock is high, the output can change, and if you have D flip-flops, the output only gets stored on the rising or falling edge of the clock. Yeah, that's basically what we learned. Yeah. The black plastic, this ceramic variants too. Okay, yeah, thanks. Good to know. Thanks. All right. So let's maybe look at the schematic really quick that he has drawn here. So I guess we are building like the A register. Let's see. It uses two 173s and then this other one, this 245, that is this three-state output, like this bus controller thing. What part are you on? We just start with the first register. We finished the clock module. So far, and then we watched a couple of videos on how flip-flops and stuff works, and now we finally start with the register. So today on stream, we have been live for almost 2.5 hours. I want to build the first register now, and then we continue another time. All right. Okay, so we need 2 of the 173. Actually, maybe I should leave this on there to keep them together. You are still on category just chatting, is this right? Yeah, I mean, doesn't matter. I'm kind of experimenting. The just chatting is just so huge. I mean, Yeah. We talked. Were you there when we talked about that the other day? I don't want to repeat myself if you already heard my why I'm on just chatting. And so this is the so this was the register flip-flop thingy, and this chip here is the bus controller chip kind of thing. It's the 245, so that one is used to basically, well, what were the terms? I don't want to use the wrong terms. To enable? Was it just enable? If you read or write on, like if you write it to the bus or not. Actually, this chip is theoretically not needed. Ben Eater only uses it so that we can see the output, the current state of the registers, what is stored in there with LEDs. Do you have an IC puller? Because they will come in handy if you want to remove a dip chip bending the pins. No, but I have something like this. You know, like you can shove it under. You can like shove it under the ICs, I guess, and lift it out. Should be good enough. First time here. Okay, so the reason I thought I streamed before on Science and Technology. It absolutely makes sense to stream on there because that's where it kind of belongs in terms of like keeping it like tidy and properly categorized, kind of, I would say. But just chatting has kind of evolved into anything basically streaming. Anything that is not necessarily just gaming is in just chatting. It's so massive. So it's kind of an experiment to see if that changes if people like stumble into here. Because like the problem with the science and technology category is that only people that want to see programming streams or stuff like this go there and to check it out. But I hope that maybe random people who have never thought about electronics or programming kind of stumble into the stream and think, whoa, this is kind of weird and interesting. So that's kind of my hope. Yeah. So let's see. He put this all the way over here. And in a way, it's just chatting, right? Like we are chatting while, I mean, that's the idea of the stream, right? We are building this, but also I want to just like, you know, talk with you and just chat about stuff when it comes up. God damn it. Come on, go in there. Okay, there we go. Is he also chatting or just die-hard programming? I mean, he's Zoding is programming pretty hardcore, but also chatting. I mean, everybody who is like developing on Twitch is usually also talking a lot. Like Adam or Zoding are very good, I think, at that. I mean, but you know, it's just an experiment for me. It's not like I care really that much about it. Hardcore chatter. Okay, so wait, so let's go back to the previous video because in the
So last video we
sorry, let me mute that. In the previous video there were some wires underneath. I need to check again. What does he connect there? Definitely want to look up again on the schematic what exactly he did there. Let's see, is there a good picture for that state? Oh, do you hear the thunder outside? Thunder is slowly coming here. I think I read that it's supposed to start raining around this time now. I'm wondering if I should make streams of me doing PCB designs, but I don't think my work will like it. Yeah, I guess that's a problem. But if it sounds like I assume you are a professional who does PCB design professionally. I would love to see a professional PCB designer doing that from work in some way, like sharing something. If there's part of your work you can share, or working on a personal project, and you can share that with your experience of doing that at work as well. Super valuable, I think, something like that. All right, so okay. Cool. So the first chip here is maybe I should definitely pull up the 245 LS245. The other spreadsheet, I just want to see the pin out. Okay, so there is the direction pin and the VCC pin. So pin 20 up here in the top right has to be VCC. And as he mentioned in the video, he is connecting the direction pin also consistently into one direction, because we are not reading or writing into different directions. We are just writing out from here. So that's why the direction is also hardwired. That's why we see here the two connections from VCC going into the top two like pins. Stop. You should subscribe then? What do you mean? Oh, you mean subscribing to Zoring? Yeah, have I subscribed to Zoring before? Randomly sometimes I just like use my Twitch Prime if I don't forget it on some people. I'm not sure if I have used it on Zoring. Well, he even has an emote related to PHP. Yeah, I saw that. That's great. All right, so let's continue. I'm wondering if I should replace this camera. So this is like the Logitech camera, but if I had one that I could like zoom in this kind of sense, that would be so cool. Let me know if you want to make this with 256 bytes of RAM. I made a Reddit post about it. Oh, then maybe I saw your Reddit post actually, because I looked into that a little bit as well. I haven't looked up exactly how it works yet, because I still don't quite understand how the architecture works. But yeah, it's definitely a modification kind that I want to later do at some point, for sure. So super curious about this. It's super cool that you are here as well. Thanks for checking, coming by. Yeah, it makes it so much more useful. Yeah, so my dream setup, like in the end, what I'm kind of imagining, like my goal, once I've built this, I want to add the more bytes, and I guess also a bit more instruction, whatever is necessary to run something simple, so that I can put it like in the background of the stream, and then have like chat message, and then also create like a serial in, like just with an Arduino that can like place single characters into a register or something like this, that then the program can then read from. And then I can like pipe in chat messages or donations or something like this, and let them interact with it. Something like that. That would be cool. You could buy a macro lens for zooming. Yeah, sure, but I mean, this is like a Logitech webcam, you know, there's like no lens on it. I do have another DSLR over there, but it's a Canon one. It doesn't have an HDMI thing. It only has like USB, but I thought about it as well. I might try it maybe on a stream tomorrow to see how it works with the DSLR. I just wonder if maybe yeah, the heavy DSLR, like this is attached very jankily to my to a kind of a bookshelf thing. So like this heavy arm is attached to like a thin board of the bookshelf. So that feels a bit tough, but maybe I will experiment with it. All right. Okay. So stop procrastinating. Okay. So we need. You made an assembler in Python that works great. Yeah, awesome. Yeah, that's also something I want to then play around with. Did you add also any different instructions, or has your machine just the basic instruction that Ben Idra also implemented? That's another thing. I like I said, I don't quite know yet. I haven't watched the whole series beforehand. I just clicked in a couple of videos and decided I want to build this. So I don't know exactly what the capabilities of the machine are. I just here and there, reading Reddit posts like yours and just like scanning over it, I kind of got a few informations about it. For example, that's where I heard about the 16 bytes of RAM and all that kind of stuff. But I don't know exactly, and also that there's like very limited instruction, and I think people added more instruction or something like this, if I remember correctly. A new target for GCC. Yeah, that's the problem. That will be a bit rough because you have big size constraints, and then also, you might need to add kind of a stack and stuff like this. I don't know. Seems pretty tough. I added a subtract immediate. I don't think Ben had that. Ah, cool. We want 2 more of these one basically, and we want the same one in black as well. We want 1, 2, 3, 4, kind of 5 in black of that same length as well. So let me prepare. Two red and now some black. Is this the first register or was on the phone for the last 40 minutes? Yep, that's the first register. My next goal is to add a simple LCD display to display ASCII characters. Yeah, I saw some photos of other people's versions that also had that. That also seemed like a cool addition. Maybe also some kind of input. Yeah, and I think I also saw somebody adding like a like a controller or something like this to it. Yeah, as I mentioned, I definitely want to add like a serial kind of input, like just, oh well, not fully serial, just like, one register, like one input register, and I mean you can use it then for anything. But I thought about like using it to basically stream in characters from an Arduino, which then can like, you know, kind of like be used to forward messages from the PC to the CPU. I got a brain freeze. Do you know anything about undervolting CPUs? What do you mean by that? Do you mean for like glitching, or is that like a weird kind of performance thing? I don't know. Oof, please be quiet, but oh, let's quickly check again. So these two are the register ICs, and there he connected pin 1 and 2. So what was that again? Pin 1 and 2 were the output control. Okay, yeah. So these are constantly set to output. Wait, yeah, they are put to 0. Yeah, that was an inverter. Okay, makes sense. I've actually never heard of undervolting a CPU to save power consumption or something like this, but I guess makes sense. I just never heard of anybody like doing that, I guess. Interesting. Are modern CPUs not very great with like power efficiency anyway? Like if it's not needed, they will like power down extremely to energy saving. Or I guess that's only true for the mobile processors maybe. Ah, crap, I screwed that one up. Oh no, I screwed another one up. I can't wait for my wire stripper. Hopefully I bought the correct size and stuff for it. So has been either put anything like on this side of the breadboard. Is that free? Because I feel like I want to maybe put the LEDs not sticking out like that, but neatly placing them like on this side or something like this. I need to check the big overview for that. I did it on my laptop so I can watch the stream for 11 hours. How do you manage to live with Linux? I often try to switch to Linux from macOS, but it fails so inconveniently. I ended up Googling a configure longer than being productive. Well, actually I also work with my Mac. So here's my Mac. This is just my Linux machine, which I'm just using to watch YouTube videos right now. But generally, I do like security consultants. I do like code reviews and stuff like this. And sometimes I just need a Linux machine and for my like the productive works of like reading emails and chatting with colleagues and all that kind of stuff. I also just like the Mac because it's like very, very nice for that kind of stuff. But for doing actual most work, I kind of need some kind of Linux environment, so I use Docker a lot, but I also use VMs, and sometimes I also use a physical laptop, depending on like what's going on. So I have so because I have MacBooks already, I put on the ThinkPad Linux. Yeah, wait, what are you using to strip wires right now? Just old school, like a clipper, and just, hold it at like this size and then just like pull. And sometimes I accidentally strip too much and destroy the cable. All you spoiled kids. Back in my days, we only had this kind of clipper to strip wires. Right, this goes up here. You can also use an X-Acto knife. My gosh, this bot is constantly killing the the talk about the wire stripper. This way I will never get partnered. Twitch will see that we only talked about strippers. Oh, thanks for the bits, critters. And yes, I think somebody made the crisis joke already. I think even in the first stream or something. Back in my father's day, they didn't even have the breadboards. They were like using straight up cardboard. By the way, Soding reminds me again that this time can please somebody remind me that I host somebody when I go offline. The past 2 days. I always forgot, and when I'm off, I realize, crap, I forgot again to host somebody. What a waste. I don't want to forget it this time. Okay, so let's see. Got the 4 red ones and the 5 black ones, and now we need this very tiny jumper here in black. An Amiga case for it. I guess that could be kind of cool. Well, I kind of want it to be open, you know, not in a case. So we'll connect. Oh wow, that was already too wide. That must be really tiny. Okay. Thanks again for the cheer critters. What's the goal for this computer and what speed will it run at? Well, the goal is educational. I just want to better understand how the actual low-level components of a computer work. At the same time, learning a bit more about electronics. Plus using it as, you know, to have a stream and just to have a something like the stream is also, you know, part of this kind of project, so that also has some value for me. And it's not supposed to do anything besides just like execute small programs. I think it's a kind of a cool art piece when it's like done. You can put it in the background and it will execute and blink in weird ways. I think that's kind of cool, and maybe we can also make it chat interactive at some point. And that's about it. And the other question was, what speed will it run at? We measured the clock yesterday, so this clock module can go up to 500 hertz right now. I don't know if theoretically the CPU itself can handle that or can even like go much higher than that. I don't know, but that's something we can try out. We can like try to figure out the max speed once we have the whole CPU. We can see when it starts glitching or something. By the way, do this stream alerts with the sound work now? I can't hear the sound because I'm not connected to that PC. Like these headphones are connected to my laptop. They should. Hopefully that works now. It would be pretty. Yes, the sound works. Cool. Is the sound okay? Is it like too loud? Is it like, I don't know, annoying? Or it would be pretty cool if you could send it a calculation and return the result and you saw it processing it in the background. Yeah, something like that. That would be really cool. Because I like CTF challenges, I think what would be kind of cool would be to have like, you know, some kind of hidden program that you need to enter a certain like password or something like this, have it in the background, and then chat messages can basically are attempting to input something, and you would be able to see the execution of the CPU and whatever it does. Yeah, you can then slowly try to figure out what the correct input is. That's kind of like the idea, or that's one idea I have. Let's see if we can do that. Thanks again for the cheer. What's up, doggy? Did you hear the dog yowl? Okay, so this connects these two pins. What are these two pins? Why are we connecting them again? So this is pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Pin 10. We are connecting pin 10, that is the part of the data enable. So yellow is data enable. There's this AND gate, this NAND or whatever it is called, AND with the inverted inputs beforehand. So that is 9 and 10, and that I guess makes also sense looking at this. So we have the 10 connected here, and then this also bridges it over to the 9th pin. Yeah. Okay. Do you guys think that the stream misses like music? Because I don't know, because sometimes I'm just like cutting wires or something like this, and I don't know what to talk about. So I wonder if I should have some chill music. My kind of opinion is that I don't put music on, because then everybody's free to just put, additional music quietly into the background themselves, whatever they want to listen to. Yeah, no music is best. Yeah, okay, agree. Kind of agree. For that reason, like if you want to listen to music, you can add a bit of music in the background as well. Oh crap, I accidentally damaged this cable in the middle. I really hope I have bought enough wire, so I have one additional spool for each color. I hope that's enough. Ben's original pod list only requires one spool, so I hope I'm okay with that. And what kind of music I like? Well, I don't know. I like a variety of music. It's all different. Just on stream, it would have to be some kind of copyright-free music, just because of German copyright laws. I would have to pay a lot of money to be able to stream regular copyrighted music. And so maybe I would listen to some kind of like chip tunes or something like that. Would this machine be fast enough to like control some kind of noise chip to generate some kind of, I don't know, as a simple tracker or something like that? That would be also kind of cool if it could play music. But that definitely requires a bit more RAM to store kind of the... I definitely also need to get my pliers with the pointy ends to apply these kind of small stuff more easily. I've also gotten rid of the dip switches and built an Arduino to automatically program the RAM. Isn't Benita also, did Benita not do that as well? I also heard about that programming by hand stuff and then using an Arduino to program that automatically. Yeah, I definitely also want to do that. To solve the issue of all the cables going to the Arduino, maybe it makes sense to build a simple Arduino circuit on a breadboard itself instead of using an external one, or maybe use, you know, like a kind of socket to socket the Arduino onto the breadboard. Doesn't that exist as well? And then you can have kind of clean wires also going, like straight wires and not like these other kind of things. Jumper wires. Or did you already do it without jumper wires? If you like chip tunes, you should check out modules.pl. Oh, for sure, will do. Thanks. Sammy, do you mind closing my door? Okay, so now we have the yellow connection. We need another one over there, but actually almost done. You can store only the notes and make noise with the beeper. Yeah, that makes sense. Krithos, thanks again for the cheer. You should turn off autofocus on your main camera. It keeps pulsing when your hands are not in shot. I think from the blinking LEDs. From this camera here, I kind of want focus to like show like up here, but yeah, I guess maybe that makes sense. I will experiment later today with a DSLR camera instead of the Logitech thing. I hope this arm can hold that. Oh, I think Ben only used the Arduino for the EEPROM. Wait, what did you use it for? To program the RAM as well. Ah, gotcha. Yeah, I guess if you 256 bytes instead of 16 bytes or like, I don't know, 10 bytes for a program, that makes sense. Okay, so he also connected here pin, like what is it, 15 together? Pin 15. Oh, that's a clear. Okay, yeah, the clear. I don't understand Twitch. What does it mean? Critters cheers shared rewards to 3 others in chat. What does it mean? Okay. Who knows? Thanks again for the cheer. You are at 1,000 cheers overall. Thanks so much. Oh, now you're at 2,000. That's very generous of you. Thank you so much. But what does it mean that you shared rewards to 25 others in chat? What are these kind of rewards? What does it mean? Oh, it was 10 people. Thanks so much. And I'm sure whoever received some kind of reward is also thankful. I don't know. Okay, so we got that part done. Oh my gosh, I'm so slow. We are over 3 hours again. Oh my gosh. Wait, did he add a white wire here as well? Is that going from like pin 7 to 7? 7. Oh, 7 is a clock signal. Okay, and he used a white wire for the clock. All right, and let's do that too. Holy shit, 2,000 bits. Thank you very much. So ProGJ, you received something from that now? Or why are you saying thanks? Like, what did you get? Bits is just like a donation. It's just basically you can buy bits for money, and so basically it's a donation to me. But I don't understand what rewards are. A new emote? What kind of emotes do you get? Is this are these like Twitch premium emotes or something like that? So we can use like okay, I don't know. So so I have here like unlocked. I got this emote now because he cheered. That is weird. Thank you so much. I don't understand what it means, but that I guess is cool. There's a Pikachu. Is that also like an unlocked thing? It says it's like unlocked. I don't know why it's unlocked for me. Where's the pride flag? I guess I don't have that. $4,000 bit. Now you make this awkward. I don't know how to react to stuff like that. Thank you very much. It's really appreciated. And maybe we will soon figure out or I will soon understand what this whatever unlocks. Okay, I also want pride. I guess I have pride balloons. The emoticons under unlocked. I also have quite a lot of unlocked stuff. I didn't know that this is like related to like bits or cheering or stuff like this. Okay, like that's kind of weird. I've been hanging out on Twitch so much recently, and that I, for the first, hadn't really noticed this before about the unlocking. Is kind of interesting. Yeah, I also have balloons. Okay, maybe that's those unlocks. That's cool. 8,000 bits overall. Wait, how much is a bit again? That's $80 or more? Well, thank you very much. It's highly appreciated. I feel very honored that you think I provide enough value that deserves $80 from you. That's very nice. Thank you. If you continue at the current rate, dude, that $80. Okay, so this stream earned me more than a typical live overflow video earns in ad money. Just to give you a little bit of context, and this with like 60 viewers, right? Like, just the relations here. Oh, thanks for the sub, Jazels. I can tell you how much, for example, which is a kind of a bad example because it's obviously not performing well because it's a very technical video. But ad revenue from my latest video, which I released on Sunday, is... Sorry, give me a second, it's loading. Donations through Twitch or Patreon. So Twitch depends. So with the bits, I think actually the bits cost a bit more when you buy them, and then it translates literally to 100 bits $1 if I understood it correctly. So it just costs you more when you buy the bits, and that is the part that Twitch takes, which I don't know the percentage of that is, and for subscriptions, because I'm an affiliate, that means it's 50-50 if you subscribe. If you have Twitch Prime, you can subscribe for free, and I still get the sub thing. So if you have no use for your Twitch Prime, consider it using it on some streamers. Doesn't have to be me, but it's wasted money if you don't use it on somebody. So use it on Zoding, use it on Adam, or some of the other cool streamers. And then Patreon, I forgot what the percentage of Patreon is. Is it like 10% for Patreon or 15% maybe? Something like that maybe? Okay, so wait. Analytics. So wait, it doesn't even show up in my earning videos. Oh my god. So last week's video, that was the JIT video. Oh my gosh, it's not wait, where is it? Okay, so but also like this video is obviously not well performing because it's a very technical, boring video. It's not as clickbait. Okay, so last video that I uploaded on Saturday so far made $11. Just to, you know, it's YouTube rich money, the ad money. So you know, like the size of my channel couldn't be done professionally or anything just from YouTube ads alone. Even though, you know, I have that many subscribers, I have my videos don't get watched as much as I have subscribers. It's understandable. It's a very technical channel. It's not that entertaining and stuff like this. So absolutely makes sense. But that also means like that you really don't earn really any money from a channel like that. However, on the other hand, Patreon is then fairly strong, I would say. I earn, you know, more per video from Patreon support. Basically, it's like the ad money is like negligible compared to the Patreon money. It's still not enough to consider a job. I explained that in my update video, if you have seen that. It's still like way below minimum wage considering the time I put into the videos, which is fine. I'm not complaining. I do it for fun. I can stop anytime. So there's that. Yeah, and so it's quite interesting. So now that I have like this affiliate thing enabled on Patreon, on Twitch, to be able to receive like bits and subscriptions, the past few streams have been way less work. You know, it was 3 hours, but 3 hours I don't get very far with a live overflow video. So doing a stream like this has basically been a much better hourly wage than my YouTube videos are with 300,000 subscribers. So it's crazy with how small audience on Twitch. I mean, Critters was kind of an exception now. That's not like that would happen every day. But I've seen it like other streamers kind of make it work with fairly low view numbers, which is impossible on YouTube. It's just like on Twitch because the donation system and the subscription system is so part of the whole Twitch experience. I think viewers and there's also a much more closer relationship, so people are more inclined to pay for it, to kind of convince somebody to just even pitch in $1 per video that I work on multiple days or something on YouTube is so much harder than to ask somebody to like subscribe with Twitch Prime or something like that, just to you know, it's kind of interesting. Yeah, it's more about how someone would get his donation most effective to you. To be honest, like in the end, like I have to pay taxes on it afterwards as well. There are payment fees to transfer the money from, for example, from Patreon to my bank account and stuff like that. Like stuff eats that up anyway. I'm actually not optimizing in that sense. I don't think that it makes much sense. I guess your audience also use more ad blockers. Yeah, but I also encourage you to use ad blockers. Use ad blockers. Stop not using ad blockers. I don't have a PayPal account exposed because that makes accounting in Germany really difficult, or at least my accountant told me he doesn't want to deal with single payments on PayPal. That's why I like to go through something like AdSense or Twitch that just aggregates all the payments and then gives you one payout that is easy for accounting, rather than having single like $1 donations or something like this that you have to put into your balance and accounting, and then like your monthly and yearly accounting work in Germany. It's so annoying. it could all be automated, but my accountant has mentioned that PayPal is kind of weird and difficult or something like this. It's probably not a big deal, but I haven't had the head to deal with it yet. Okay, sorry about that rant. Let's continue with this. Okay, so basically we need it in blue and green. Now these connections here. So we need always 4 sets of the long ones and the short ones. All right. And we go from the second pin up here to the third pin here. So we cut like here. 1, 2, 3, 4. If I pay you as a European citizen, you don't have to pay taxes. Yeah, sure, no taxes, but no VAT, VAT tax, but you still have to. I mean, business tax in my case, or if you are freelancing, it's your income tax. Obviously, that comes as well. You just don't pay VAT. And you still need to file everything in the bookkeeping. Every incoming transactions has to be, properly filed in the bookkeeping software. And that integration with PayPal is apparently, at least my accountant has mentioned that they have no experience with that. I'm sure, if that becomes kind of an important part of what I do with this business here or something, then I'm sure I can convince them to look into it again. But for now it has, I'm still trying to figure out how all this business stuff works, so it has kind of a low priority. Okay. I think you should try to follow the schematics instead of the video. It makes more sense. For instance, I cannot see the resistors for the LEDs in Ben's video, but I can see them. Oh yeah, for sure. I cross-check with the schematics. It is just kind of easier to see how he nicely arranges it. But yeah, definitely. I will also rearrange it differently. I want to put the LEDs probably on this side here, nicely. So they don't stick out like crazy like his one. But I need to check again on the overview if he is using that for something else at some point, or if I can use that for the LEDs. Yeah, thanks, and bye, Mr. J. The business stuff is very easy. If you get more money, if you channel it through the business, you can do that, and if it doesn't, then you don't. I don't know what you are talking about. Tax evasion is not illegal. What are you talking about? Of course tax evasion is illegal. It's punished up to, depending on the severity in Germany, fines and jail time. Are you planning on doing game streaming? I don't know. I don't know. Maybe I play some Apex sometime on stream. But for the near future, this is the content of the stream here. I mean, that's also why I created the random overflow YouTube channel, just because I want to kind of like have no pressure of what I'm doing. Taking a little bit back my just like creativity. I feel a certain pressure with the videos and the content I put out on the Live Overflow YouTube channel. So having another format where I can have a bit more freedom is kind of what I'm looking for. Fear. Don't pressure people into cheering more. This was extremely generous already and absolutely unnecessary. So that is more than appreciated already. Okay, so we have the 4 green ones, and let's do right away the 4 blue ones as well. LEDs? Not yet. Yeah, no, I'm still working on the regular wiring. I'm really curious what country you are from, Pro GJ, that you say tax evasion is not illegal. Like, how do you imagine the real world works? And you know, the last thing I want is to get in any legal or like trouble with anything I do. You know, I'm so stressful already to have like the responsibility of you know, being a freelancer and stuff like this. The last thing I want is having some kind of legal fight over something stupid. So I rather pay maybe not as tax optimized, you know, could be better, could do the stuff myself, don't need an accountant, but making sure that no unnecessary that no unnecessary like legal issues come is worth a lot. Tax fraud, unequal tax evasion. I think you try to okay, maybe it's a translation issue. Tax evasion, the translation of that in Germany is very illegal. Tax optimization, if you are moving in the legal limits of lowering your taxes, for example, by writing stuff off that you buy, that is a legal way to lower your taxes. That's fine. But if you evade taxes, for example, by not reporting your income to that business, or by wiring the money to me directly rather than through the business, even though it was clearly related to the business, then that is clearly evading taxes. It's not reported stuff. Yeah, okay, so it's a translation issue. Tax evasion is what you call tax fraud. I was thinking tax fraud of more in the sense of that you are, for example, deliberately like report expenses that weren't there at all, just to get like taxes back or something like this. But whatever, it's just semantics at this point. I guess we mean the same thing. But yeah, anyway, any money that is flowing towards me has to be properly put into bookkeeping by the accountant and reported to the tax office. If that is somehow optimized with write-offs and no need for VAT or something like this because it's coming from the EU, sure, that's fine. But in the end, there will still be business tax on it, and then also income tax if I claim it from the business. Oh, Rally Security, nice to see you again. How you doing? Are we talking about the Irish double triple tax bouncing with the Netherlands? Oh. I've registered a heavy, boring, inefficient German GmbH, and I'm not doing anything weird. I just don't want to be in any trouble. I just want to be left alone and let me do my stuff, please. It's so annoying. Why can't we just not all have fun and somehow something magic takes care of the taxes? Being employed is so chill about taxes. It just works automatically. It's so nice. That is such a big reason for me that why I would want to maybe be employed. Just for that ease. I'm not sure if it's anything to be congratulating about. It's, just adds work. Okay, so let's see the schematic really quick. So we are connecting here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So pin 9 is connected to pin 6 of this one. 1, 2, 3, 4, 5, 6. Okay, yeah, that's correct. And there's nothing special about creating a company either. Just register it. If I could have earned money without registering a business, I would have not registered a business. I know one idea that promised only fun and no economy worries. Well, we can still have hope, It's actually not hacking GmbH, it's actually security flag related to like capture the flag and IT security. Toading using your own emote. It's not CTF GmbH, it's security flag GmbH. but the name was like inspired from CTF basically. Doesn't this look nice? Doesn't this look cool? Okay, and so up here we then connect 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11. Is 11 already connected? 11 here is connected to 11 down there. 10, 11, and so 11 down here is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 here. Okay. Now we can look you up in the German company register. Well, it's actually also in my YouTube description because German law requires to disclose you that. It's also on my website and everything. It's the same with Germany. It's all registered public knowledge, and also by law I'm required to put that on my YouTube and on my website as well. Oh, hi Beacon, Beacon Bin. So I'm building the 8-bit computer or basically follow along Ben Eater. Wait, let me rephrase that. Ben Eater has a YouTube channel where he's building where he built an 8-bit computer on breadboards to learn more about how computers work. And so here on stream, we are watching his videos and follow along and also build that. We try to replicate that also with measurement gear and all that kind of stuff. And as of right now, we are building the first register. The first register component. The stuff you see blinking here is the clock module. So this allows that's the clock of the CPU, and we can change the speed of the clock here. So that's the summary of that. Yeah, German laws suck. I hate them. Okay, so the next one is connected to like 12 is also connected to 12. Okay, so it just goes up here. No, you can't register it on a PO box because German laws. I told you the laws suck. It's really stupid. It must be a legal address, and a legal address has certain requirements on what that can be, and a PO box does not fulfill the requirements of a legal address. I should have. Let me think. I guess it's fine. Just considering how I should arrange these things. Is that one of his other videos he's working off in the bottom left of the screen? Yeah, so that is the bottom left of the screen is the video by Ben Eder that I'm just like copying right now. So yeah. Okay, so now the shorter wires. Oh my gosh, this is going so slow. We are approaching 4 hours. I'm so slow. Okay, so basically this is the same connection from the third pin from down here goes up to here. Today the stream will be shorter. Yeah. Screwed that up. Let's see, is that the good length? So that would go in here, over to here. Maybe a bit too short, okay. But now I know how long I have to make it. And we need 4 of those. Is it intended that the breadboard connection knobs are not facing in the same direction? Breadboard connection knobs. I don't know what you mean with breadboard connection knobs. If I were to send you a €10 bill through the mail, would you register it in the company income? If you send it to the company address, yeah, for sure. I mean, I wonder how you declare that. That's the whole thing. Like it's probably like a tip or something like that. But yeah, I would have to do that. Try to explain the tax office why you have a cash tip in your online business. That's kind of they will just get suspicious, and then they will send like a what is it, like a review of everything, and then they will come and search the whole place and stuff like that to click them together. Not facing in the same direction. Well, they face in the same direction. What do you mean? Like, oh, you mean the direction this module should be used? I have not paid at all any attention to that so far. This module seems to be the same as Ben Eder has done it, but I have no clue if we built the clock the wrong way around. I have not thought about paying attention to that. Oh my gosh, this is making me feel bad. Oh my gosh, I'm so scared. We did it! It's the correct way. You can put LEDs directly to the right of the chip. The space to the right would be taken by the flags register. Oh, you put here a flags register? Well, but okay, so then I cannot put the LEDs there. Because I need the flags register there. Okay. No, that's enough space. Okay. Do you? Yeah, I will look it up in the video. We will probably not do the LEDs tonight. I really want to stop streaming. I want to have an evening. I'm out for today. Okay. Thanks for hanging out. Have a nice evening. I need a sip of the Club Mate. Good idea. Good thinking there. So if that goes in here, where can you buy a Club Mate? At the store? I looked it up, and the only store that sells it in Eindhoven is some liquor store. Yeah, I guess they must have imported. It's from Germany, the drink. Anyone in this chat remember the Food Babe series? Did you like that one? Did you watch it? You like my videos? I keep recommending them to everyone. That's nice. Thank you very much. What kind of videos do you usually recommend them to watch? Do you tell them watch this particular video or this series or something like this? I would be curious what kind of what are the videos that make you recommend them? The game one and the CTF ones, also your hardware ones. Okay, that's great. That's a good collection of basically everything I do on the channel, so that's nice. Okay, green looks done. And then we connect the third pin here. With up here. I watch adult stuff, but more advanced stuff, and I also want to make a Twitch channel making my strange stuff, but I did not know if it was allowed, but you gave me the answer. Why do you think it wouldn't be allowed? I mean, as long as you don't show like game cracking or, you know, other kinds of illegal stuff, you should be totally fine on Twitch. The place up here gets very tight now. Why do you have the clock module open on your ThinkPad? It's not the clock module that is open, that's the register there. And we are building here the register. Or did you mean this one here? The other tab? This was just open because we looked up the orientation of the breadboard earlier. Do you have any previous experience with boards and stuff? Well, yeah. I'm an amateur. I played around. I have breadboards already before I've owned this. I can make like an LED blink and stuff like this. Very basic amateur knowledge. Nothing more advanced than that. So that's, yeah. So I do this also here to just learn more about it. I made all the do you know, my gosh, I need fresh air. My head is not working anymore. I can barely read chat. You do know that it does matter if you use GND of the breadboard for VC and the other way around. I mean, it's just an indication. What are you talking about? Yeah, of course, it's labeled. Have you ever considered working for big companies like Google or something? What do you think about it? Yeah, for sure. If my life has gone differently, I would have totally tried to apply to Google or Facebook or something like that. I think they are great workplaces. And maybe if my life takes a different turn, I might. I mean, right now I try to make self-employment and stuff work. But if that would ever fail, or I want to go back into employment because it's too stressful or something like that. That's something definitely I would like to do then. I personally prefer such companies over something like a small development place or something like this. Okay. Let's see. Just a quick sanity check with the schematic. Up until port 18. Yeah, that's correct. That's what I just was count. That is what I just was counting. How did you start self-employment? Wasn't it scary at first, or did you get sick of employment? No, so I I was my gosh, sorry. My brain's starting to slow down considerably. I was doing a dual study program, which means I was employed at a company and doing my bachelor's degree. And during my bachelor's degree, I kind of got into security. And towards the end of my bachelor's degree, basically was like a perfect match. A friend recommended me to somebody who was looking for freelancers and recommended me. And so I just accidentally ended up getting into that. At the same time, I was also considering going into a job or continuing university. And I was actually applying to some regular jobs. But then, again, this freelance gig happened because of the recommendation. And basically, since then, I've been working the same thing as a freelancer. And decided then to do university on the side. So I'm still in university. I'm a bit slow now finishing my master's degree because I've been working. So that's my main freelance work. That's where I earn my money. That's what pays for all of this here. You know, YouTube doesn't pay anything basically compared to what I earn as a freelancer. So this is all money that I put back into my hobby of creating videos. And then in the last year, YouTube has also reached numbers where I could think of maybe I can also earn money with that stuff as well. So so just over the past year I was kind of thinking about that more, and so now I'm also trying to see if I can build something out of this YouTube thing that I've been doing. So that is like this company that I created for it. Nothing special. It just registered so I can earn money with it. So yeah, so these are my two freelance self-employed kind of things. I have the YouTube thing that I try to build up. It doesn't earn enough money to consider it my job. It doesn't compare at all to any salary any developer or anything would get. But you know, I built it myself, so I try it out. And in parallel to that, I still work I also want to keep working as a freelancer, doing security things. So I don't deal with that clients directly. I only work for companies that are looking for freelancers to help out. And so I have connections built. Like it started with that one company, and then I've got some other connections through that. So I'm just like a freelancer on demand for stuff, basically. Do you think you would... wait, sorry. There were, do you think you would ever do a PhD? There was a time where I was seriously considering it. I think at this point in time I just have too much other stuff going on that it doesn't fit with my life right now. But it's kind of like not off the table. It's not completely off the table, but probably not at this point. Again, life might change. Things could change from one year to another, and then maybe PhD is a good option again. Life just has taken a different path for now. Okay, so this is mostly done how Ben Eder is done. The LEDs are missing, but I kind of want to put them on the other side there. I really want to stop streaming here for now. There's only one other thing I want to do before I stop the stream, and that is I mentioned it before, I'm considering putting the LEDs here on the side, and because he has here like single spacing and they are sticking out and it kind of looks shit, I want to put them like nicely onto the breadboard, but I'm unsure about the space, and so I want to look up again the whole picture of it to see what he places next to it. Now somebody in chat mentioned that he will put flags on the side here, so I wonder, I mean, if there's maybe one chip for the flags, then fine, but I feel like there could be, so I want to check that out really quick, and then after that I stop the stream. I streamed for 4 hours. How is this going? I had this goal of streaming definitely not as long as yesterday, and suddenly it's longer. Oh. If I keep that up, I will not be able to keep a regular streaming schedule. It will be too much. I have to limit it to like 2 to maximum 3 hours. Otherwise, I will not be able to sustain this. I have other responsibilities to take care of. I should be writing a master thesis right now, but you know, procrastination. You know, when is the best time to start a new project? When you have deadlines to write a master thesis. What am I doing? Overview. Does he have a nice picture? I guess not. Okay, wait. Then I guess we have to check out the video itself. Let's see. Let me put the laptop there, and then we can look together. You enjoyed the stream? Oh, that's nice. Thanks so much. I feel like I'm a little bit too tired and a bit more irritated or annoyed than the previous days. So I hope it didn't feel too bad. Really just set an alarm. Yeah, I keep an eye on the time anyway. I'm not I knew when the 2 hour was passing. It's just like, what am I gonna do? Good. I don't want to finish the LEDs right now. You know, I need to draw this out for content. But let's again check here. So here's one of the registers he built, and here's the other register. Oh, and the flex here is just a single register that he put there. Yeah, seems like we have certainly enough space here for the LEDs on the side. Perfect. Then we do that tomorrow over there. Right next to it here, a row of LEDs. That would, I think, look really nice. Okay, any remaining questions, anything you want to say? I give it like another 2 minutes or so, and then I will wind this down. Maybe let me show you what we built today, again in like a close-up. So here's the register module. It's just a lot of wires connecting the different chips. As a quick recap, these two are 4-bit registers, so they can be set and they keep their value based. They can be set based on like some enable line and stuff like that with the clock. We looked at flip-flops, whatever, you know what it's about. So these are each 4-bit, and so that's why you have 4 lines going over here. One line is the input and the other lines are the output. I think up here are the input lines, I think, and this are the output lines, because this is where we attach the LEDs to, if I interpret this correctly. Maybe we can have a quick look into the schematic again. Pin 3, 4, 5, 6 are the outputs. 1, 2, 3, 4, 5, 6. Yeah, so these are the outputs down here. Yeah. Thanks for the nice compliments and words. Feels good. Your register is finished. You may rest now. Yeah. I missed the stream. Sorry about that. It wasn't a too particular good stream today. I was very tired and we had to watch a lot of videos. So it took almost like 2 hours before we even got started building this. But from here on now on, I think will be a lot of building. Don't forget to host someone. Thank you. I would have totally forgotten it. Thank you. Do you have some kind of schedule or just when you feel like it? Not really, but I feel like it will probably be more like towards the evening. So today, yesterday and today, I think it was like 7 p.m. On weekends, I might do it earlier. However, tomorrow evening, I will head out to some meetup or something. So either I will stream when I come back from that meetup later in the night, like German time, like 11, maybe even midnight starting, or I will stream in the afternoon. It's actually more likely that I will stream tomorrow in the afternoon, so earlier in the day. Maybe I need to check the time when I have to be tomorrow at the meetup where, but maybe around like 3 p.m. or something like that, maybe 2 p.m. even. So not very, very great in case you are from the US. But I guess it's already still a bit early for US people watching. Yeah. So that's the plan. But I plan to stream tomorrow, yeah. And keep an eye out on the YouTube channel, Random Overflow. This is where I'm posting and up. So first of all, you can obviously watch the VOD on Twitch as well. But I also upload them on YouTube. So you can find here the full stream archive with just the recordings of the stream. And I'm also making kind of like super cuts. I'm just like randomly chopping out parts to make it a bit shorter, taking out silence parts and taking out unnecessary boring stuff that I'm saying. It's really not great edited or anything. It's really just a shorter cut of the live stream. It's basically the live stream, but not 3 hours long. So I hope I can keep that up with the videos. I've done it for the first 3 streams, and I will, when I stop the stream, I will not go to bed. I will have to edit today's episode, basically. So yeah, check out the Random Overflow YouTube channel as well. Okay, so let me read chat and then we will wind this down. And hosting, not forget hosting. Wait 1 second. Okay, so let me recheck it and then blah. 270 subs. Wow. Yeah, well, I tweeted it out on my Twitter. It's not like I come from nothing here, right? It was promoted on a Twitter account with 25,000 followers, and I kind of also, I think, mentioned it in the community tab of my main YouTube channel. So it's not a surprising number. It's yeah. Yesterday I had 27 subs, but I tweeted it out today. So I all those subscribers are probably coming from Twitter. Don't forget your window door is open. Yeah, no worries. I won't forget. I'm not sure if it's raining right now, actually. Doesn't sound like it. Okay, hosting someone. So who am I hosting and how does this work again with hosting? I never do that. Okay, let me see. Okay, wait. I can host. Why is the host button grayed out? So in the dashboard, are you planning to do a CTF soon? I plan to play the Google CTF at least a little bit. Okay, I'm too stupid for this. So when there's like this rate and host thing on my dashboard, and there's like rate and host button, but they are grayed out, and when I go over the mouse, it's like this forbidden mouse pointer. Why is this so difficult? Why are computers so hard? I think there's a book about building an 8-bit computer. Maybe you are referring actually to the book that this series is based on. So there, so Ben Eder, the series here is based on this book. So the architecture is called SAP, Simple as Possible, and it's from an old book on computer architecture kind of thing. That's what Ben Eder bases his videos on. So it might be that book actually. Then why is it's not on my dashboard? Then why is there a host and a rate button on my dashboard? If that's not the... Oh, /host, is that a thing? Okay, /host. Okay, so who can I host? Who is online right now? Let me see. Okay, wait, I can use this laptop here to check out the channel. At some point I will become a professional too. How to use host mode. /host channel name. All right, then let's search for a channel to host. Let's see. Let's see first. Can I somehow see if anybody of my people that I have on auto host are online? I mean, I do have auto host enabled, so even if I forget hosting, somebody will be auto hosted. Israeli security, are you streaming right now? Let me check. No, not streaming. Rook is also not streaming. I think Adam is probably offline at this point already. I'm not sure. Yeah, Adam is also not online. Jamie is not online. Scanlime is not online. Okay, so that was fail. How do other streamers do this so quickly? Science and technology. Let's see. Does anybody know anybody of these streamers and wants us to host them? I'm not sure if I know anybody of them, but if anybody here knows somebody, I'm happy to leave a host there. Even your friend, even if it's not about programmer or something. If you have a random friend playing Apex with 3 viewers, I'm happy to host. Shall we host Destiny? He will be happy with his 58 viewers. Dowright. Okay, 2 people have said Dowright. All right. Okay, so I triggered the host. Thanks for hanging out with me, in case you still hear me, and see you tomorrow, maybe. And thanks again for all the bits and subscriptions and all that stuff.